Neural networks are good for learning lots of different types of patterns. To give an example of how this would work, imagine you had a 4-pixel camera. So not 4 megapixels, but just 4 pixels. And it was only black and white. And you wanted to go around and take pictures of things and determine automatically then whether these pictures were of a solid all white or all dark image, a vertical line, or a diagonal line, or a horizontal line. This is tricky because you can't do this with simple rules about the brightness of the pixels. Both of these are horizontal lines, but if you tried to make a rule about which pixel was bright and which was dark, you wouldn't be able to do it. So to do this with the neural network, you start by taking all of your inputs, in this case our 4 pixels, and you break them out into input neurons. And you assign a number to each of these depending on the brightness or darkness of the pixel. +1 is all the way white, -1 is all the way black, and then gray is 0, right in the middle. So these values, once you have them broken out and listed like this on the input neurons, it's also called the input vector or array. It's just a list of numbers that represents your inputs right now. It's a useful notion to think about the receptive field of a neuron. All this means is what set of inputs makes the value of this neuron as high as it can possibly be. For input neurons, this is pretty easy. Each one is associated with just 1 pixel, and when that pixel is all the way white, the value of that input neuron is as high as it can go. The black and white checkered areas show pixels that an input neuron doesn't care about. If they're all the way white or all the way black, it still doesn't affect the value of that input neuron at all. Now, to build a neural network, we create a neuron. The first thing this does is it adds up all of the values of the input neurons. So in this case, if we add up all of those values, we get a 0.5. Now to complicate things just a little bit, each of the connections are weighted, meaning they're multiplied by a number. That number can be 1 or -1 or anything in between. So for instance, if something has a weight of -1, it's multiplied and you get the negative of it, and that's added in. If something has a weight of 0, then it's effectively ignored. So here's what those weighted connections might look like. And you'll notice that after the values of the input neurons are weighted and added, the final value is completely different. Graphically, it's convenient to represent these weights as white links being positive weights, black links being negative weights, and the thickness of the line is roughly proportional to the magnitude of the weight. Then, after you add the weighted input neurons, they get squashed. And I'll show you what that means. You have a sigmoid squashing function. Sigmoid just means S-shaped. And what this does is you put a value in, let's say 0.5, and you run a vertical line up to your sigmoid and then a horizontal line over from where it crosses. And then where that hits the y-axis, that's the output of your function. So in this case, slightly less than 0.5. It's pretty close. As your input number gets larger, your output number also gets larger but more slowly. And eventually, no matter how big the number you put in, the answer is always less than 1. Similarly, when you go negative, the answer is always greater than -1. So this ensures that that neuron's value never gets outside of the range of +1 to -1, which is helpful for keeping the computations in the neural network bounded and stable. So after you sum the weighted values of the neurons and squash the result, you get the output. In this case, 0.746, that is a neuron. So we can collapse all that down, and this is a neuron that does a weighted sum and squash the result. And now instead of just one of those, assume you have a whole bunch. There are 4 shown here, but there could be 400 or 4 million. Now, to keep our picture clear, we'll assume for now that the weights are either +1, white lines, -1, black lines, or 0, in which case they're missing entirely. But in actuality, all of these neurons that we created are each attached to all of the input neurons, and they all have some weight between -1 and +1. When we create this first layer of our neural network, the receptive fields get more complex. For instance, here, each of those end up combining 2 of our input neurons. And so the value, the receptive field, the pixel values that make that first layer neuron as large as it can possibly be, look now like pairs of pixels, either all white or a mixture of white and black, depending on the weights. So for instance, this neuron here is attached to this input pixel, which is upper left, and this input pixel, which is lower left, and both of those weights are positive. So it combines the 2 of those, and that's its receptive field, the receptive field of this one plus the receptive field of this one. However, if we look at this neuron, it combines this pixel, upper right, and this pixel, lower right. It has a weight of -1 for the lower right pixel, so that means it's most active when this pixel is black. So here is its receptive field. Now, because we were careful of how we created that first layer, its values look a lot like input values. And we can turn right around and create another layer on top of it the exact same way, with the output of one layer being the input to the next layer. And we can repeat this 3 times or 7 times or 700 times for additional layers. Each time the receptive fields get even more complex. So you can see here, using the same logic, now they cover all of the pixels and more special arrangement of which are black and which are white. We can create another layer. Again, all of these neurons in one layer are connected to all of the neurons in the previous layer, but we're assuming here that most of those weights are 0 and not shown. It's not generally the case. So just to mix things up, we'll create a new layer, but if you notice our squashing function isn't there anymore. We have something new called a rectified linear unit. This is another popular neuron type. So you do your weighted sum of all your inputs, and instead of squashing, you do rectified linear units. You rectify it. So if it is negative, you make the value 0. If it's positive, you keep the value. This is obviously very easy to compute, and it turns out to have very nice stability properties for neural networks as well in practice. So after we do this, because some of our weights are positive and some are negative, connecting to those rectified linear units, we get receptive fields and their opposites. If you look at the patterns there. And then finally, when we've created as many layers with as many neurons as we want, we create an output layer. Here, we have 4 outputs that we're interested in. Is the image solid, vertical, diagonal, or horizontal? So to walk through an example here of how this would work, let's say we start with this input image shown on the left. Dark pixels on top, white on the bottom. As we propagate that to our input layer, this is what those values would look like. The top pixels, the bottom pixels. As we move that to our first layer, we can see The combination of a dark pixel and a light pixel summed together get us 0, gray. Whereas down here we have the combination of a dark pixel plus a light pixel with a negative weight. So that gets us a value of -1 there, which makes sense because if we look at the receptive field here, upper left pixel white, lower left pixel black, it's the exact opposite of the input that we're getting. And so we would expect its value to be as low as possible, -1. As we move to the next layer, we see the same types of things, combining zeros to get zeros, combining a negative and a negative with a negative weight, which makes a positive, to get a 0. And here we have combining two negatives to get a negative. So again, you'll notice the receptive field of this is exactly the inverse of our input. So it makes sense that its weight would be negative, or its value would be negative. And we move to the next layer. All of these, of course, these zeros propagate forward. Here, this is a negative, has a negative value, and it has a positive weight. So it just moves straight forward. Because we have a rectified linear unit, negative values become 0. So now it is 0 again too, but this one gets rectified and becomes positive. Negative times a negative is positive. And so when we finally get to the output, we can see they're all 0 except for this horizontal, which is positive, and that's the answer. Our neural network said this is an image of a horizontal line. Now, neural networks usually aren't that good, not that clean. So there's a notion of, with an input, what is truth? In this case, the truth is this has a 0 for all of these values, but a 1 for horizontal. It's not solid, it's not vertical, it's not diagonal. Yes, it is horizontal. An arbitrary neural network will give answers that are not exactly truth. They might be off by a little or a lot. And then the error is the magnitude of the difference between the truth and the answer given. And you can add all these up to get the total error for the neural network. So the whole idea with learning and training is to adjust the weights to make the error as low as possible. So the way this is done is we put an image in, we calculate the error at the end, then we look for how to adjust those weights higher or lower to either make that error go up or down. And we, of course, adjust the weights in the way, then make the error go down. Now, the problem with doing this is each time we go back and calculate the error, we have to multiply all of those weights by all of the neuron values at each layer. And we have to do that again and again once for each weight. This takes forever in computing terms, on a computing scale, and so it's not a practical way to train a big neural network. You can imagine instead of just rolling down to the bottom of a simple valley, we have a very high dimensional valley, and we have to find our way down. And because there are so many dimensions, one for each of these weights, that the computation just becomes prohibitively expensive. Luckily, there was an insight that lets us do this in a very reasonable time. And that's that if we're careful about how we design our neural network, we can calculate the slope directly, the gradient. We can figure out the direction that we need to adjust the weight without going all the way back through our neural network and recalculating. So just to review, the slope that we're talking about is when we make a change in weight, the error will change a little bit. And that relation of the change in weight to the change in error is the slope. Mathematically, there are several ways to write this. We'll favor the one on the bottom. It's technically most correct. We'll call it DEDW for shorthand. Every time you see it, just think the change in error when I change a weight, or the change in the thing on the top when I change the thing on the bottom. This does get into a little bit of calculus. We do take derivatives. That's how we calculate slope. If it's new to you, I strongly recommend a good semester of calculus just because the concepts are so universal. And a lot of them have very nice physical interpretations, which I find very appealing. But don't worry. Otherwise, just gloss over this and pay attention to the rest, and you'll get a general sense for how this works. So in this case, if we change the weight by +1, the error changes by -2, which gives us a slope of -2. That tells us the direction that we should adjust our weight and how much we should adjust it to bring the error down. Now to do this, you have to know what your error function is. So assume we had an error function that was the square of the weight, and you can see that our weight is right at -1. So the first thing we do is we take the derivative, change in error, divided by change in weight, dE dW. The derivative of weight squared is 2 times the weight. And so we plug in our weight of -1, and we get a slope, dE dW, of -2. Now the other trick that lets us do this with deep neural networks is chaining. And to show you how this works, imagine a very simple trivial neural network with just one hidden layer, one input layer, one output layer, and one weight connecting each of them. So it's obvious to see that the value y is just the value x times the weight connecting them, w1. So if we change w1 a little bit, we just take the derivative of y with respect to w1, and we get x. The slope is x. If I change w1 by a little bit, then y will change by x times the size of that adjustment. Similarly, for the next step, we can see that e is just the value y times the weight w2. And so when we calculate dE dy, it's just w2. Because this network is so simple, we can calculate from one end to the other. X times w1 times w2 is the error e. And so if we want to calculate how much will the error change if I change w1, we just take the derivative of that with respect to w1 and get x times w2. So this illustrates, you can see here now, that what we just calculated is actually the product of our first derivative that we took, the dy dw1, times the derivative for the next step, dE dy, multiplied together. This is chaining. You can calculate the slope of each tiny step and then multiply all of those together to get the slope of the full chain, the derivative of the full chain. So in a deeper neural network, what this would look like is if I want to know how much the error will change if I adjust a weight that's deep in the network, I just calculate the derivative of each tiny little step all the way back to the weight that I'm trying to calculate, and then multiply them all together. This computationally is many, many times cheaper than what we had to do before of recalculating the error for the whole neural network for every weight. Now, in the neural network that we've created, there are several types of backpropagation we have to do. There are several operations we have to do. For each one of those, we have to be able to calculate the slope. So for the first one is just a weighted connection between two neurons, A and B. So let's assume we know the change in error with respect to B. We want to know the change in error with respect to A. To get there, we need to know dB dA. So to get that, we just write the relationship between B and A, take the derivative of B with respect to A, we get the weight, W, and now we know how to make that step. We know how to do that little nugget of backpropagation. Another element that we've seen is sums. All of our neurons sum up a lot of inputs. To take this backpropagation step, we do the same thing. We write our expression, and then we take the derivative of our endpoint, z, with respect to our step that we're propagating to A, and dz/dA in this case is just 1, which makes sense. If we have a sum of a whole bunch of elements, we increase one of those elements by 1, we expect the sum to increase by 1. That's the definition of a slope of 1. One-to-one relation there. Another element that we have that we need to be able to backpropagate is the sigmoid function. So this one's a little bit more interesting mathematically. We'll just write it shorthand like this, the sigma function. It is entirely feasible to go through and take the derivative of this analytically and calculate it. It just so happens that this function has a nice property that to get its derivative, you just multiply it by 1 minus itself. So this is very straightforward to calculate. Another element that we've used is the rectified linear unit. Again, to figure out how to backpropagate this, we just write out the relation. B is equal to A if A is positive, otherwise it's 0. And piecewise, for each of those, we take the derivative. So dB/dA is either 1 if A is positive or 0. And so with all of these little backpropagation steps and the ability to chain them together, we can calculate the effect of adjusting any given weight on the error for any given input. And so to train, then, we start with a fully connected network. We don't know what any of these weights should be, and so we assign them all random values. We create a completely arbitrary random neural network. We put in an input that we know the answer to. We know whether it's solid, vertical, diagonal, or horizontal, so we know what truth should be, and so we can calculate the error. Then we run it through, calculate the error, and using backpropagation, go through and adjust all of those weights a tiny bit in the right direction. And then we do that again with another input, and again with another input for, if we can get away with it, many thousands or even millions of times. And eventually, all of those weights will gravitate, they'll roll down that many-dimensional valley to a nice low spot in the bottom where it performs really well and does pretty close to truth on most of the images. If we're really lucky, it'll look like what we started with intuitively understandable receptive fields for those neurons and a relatively sparse representation, meaning that most of the weights are small or close to 0. And it doesn't always turn out that way, but what we are guaranteed is that it'll find a pretty good representation of the best that it can do adjusting those weights to get as close as possible to the right answer for all of the inputs. So what we've covered is just a very basic introduction to the principles behind neural networks. I haven't told you quite enough to be able to go out and build one of your own, but if you're feeling motivated to do so, I highly encourage it. Here are a few resources that you'll find useful. You'll want to go and learn about biased neurons. Dropout is a useful training tool. There are several resources available from Andrei Karpathy, who is an expert in neural networks and great at teaching about it. Also, there's a fantastic article called The Black Magic of Deep Learning that just has a bunch of practical from the trenches tips on how to get them working well.
Neural networks are famously difficult to interpret. It's hard to know what they're actually learning when we train them. So let's take a closer look and see whether we can get a good picture of what's going on inside. Just like every other supervised machine learning model, neural networks learn relationships between input variables and output variables. In fact, we can even see how it's related to the most iconic model of all, linear regression. Simple linear regression assumes a straight line relationship between an input variable, x, and an output variable, y. X is multiplied by a constant, m, which also happens to be the slope of the line. and it's added to another constant, b, which happens to be where the line crosses the y-axis. We can represent this in a picture. Our input value, x, is multiplied by m. Our constant, b, is multiplied by 1, and then they get added together to get y. This is a graphical representation of y equals mx plus b. On the far left, the circular symbols just indicate that the value is passed through. The rectangles, labeled m and b, indicate that whatever goes in on the left comes out multiplied by m or b on the right. And the box with the capital sigma indicates that whatever goes in on the left gets added together and spit out on the right. We can change the names of all the symbols for a different representation. This is still a straight line relationship. We've just changed the names of all the variables. The reason we're doing this is to translate our linear regression into the notation we'll use in neural networks. This will help us keep track of things as we move forward. At this point, we have turned a straight line equation into a network. A network is anything that has nodes connected by edges. In this case, x sub 0 and x sub 1 are our input nodes. V sub 0 is an output node, and our weights connecting them are edges. This is not the traditional sense of a graph, meaning a plot or a grid, like in a graphing calculator or graph paper. It's just the formal word for a network, for nodes connected by edges. Another piece of terminology you might hear is a directed acyclic graph, abbreviated as DAG or DAG. A directed graph is one where the edges just go in one direction. In our case, input goes to output, but output never goes back to input. Our edges are directed. Acyclic means that you can't ever draw a loop. Once you have visited a node, there's no way to jump from edges to nodes to edges to nodes to get back to where you started. Everything flows in one direction through the graph. We can get a sense of the type of models that this network is capable of learning by choosing random values for the weights. W sub 0, 0 and W sub 1, 0. And then seeing what relationship pops out between x sub 1 and v sub 0. Remember that we set x sub 0 equal to 1 and are holding it there always. This is a special node called a bias node. It should come as no surprise that the relationships that come out of this linear model are all straight lines. After all, we've taken our equation for the line and rearranged it, but we haven't changed it in any substantial way. There's no reason we have to limit ourselves to just one input variable. We can add an additional one. Now here we have an x sub 0, an x sub 1, and an x sub 2. We draw an edge between x sub 2 and our summation with the weight w sub 2, 0. X sub 2 times w sub 2, 0 is again u sub 2, 0, and all of our u's get added together to make a v sub 0. And we could add more inputs, as many as we want. This is still a linear equation, but instead of being two-dimensional, we can make it three-dimensional or higher. Writing this out mathematically could get very tedious, so we'll use a shortcut. We'll substitute the subscript I for the index of the input. It's the number of the input we're talking about. This allows us to write u sub I 0, where our u sub I equals x sub I times w sub I 0. And again, our output, v sub 0, is just the summation over all values of I of u sub I 0. For this three-dimensional case, we can again look at the models that emerge when we randomly choose our w sub I 0s, our weights. As we would expect, we still get the three-dimensional equivalent of a line, a plane in this case. And if we were to extend this to more inputs, we would get the m-dimensional equivalent of a line, which is called an m-dimensional hyperplane. So far, so good. Now we can start to get fancier. Our input, x sub 1, looks a lot like our output, v sub 0. In fact, there's nothing to prevent us from taking our output and then using it as an input to another network just like this one. Now we have two separate identical layers. We can add a subscript Roman numeral I and a subscript Roman numeral II, or 2, to our equations, depending on which layer we're referring to. And we just have to remember that our x sub 1 in layer 2 is the same as our v sub 0 in layer 1. Because these equations are identical, and each of our layers work just the same, we can reduce this to one set of equations, adding a subscript capital L to represent which layer we're talking about. As we continue here, we'll be assuming that all the layers are identical, and to keep the equations cleaner, we'll leave out the capital L, but just keep in mind that if we were going to be completely correct and verbose, we would add the L subscript onto the end of everything to specify the layer it belongs to. Now that we have two layers, there's no reason that we can't connect them in more than one place. Instead of our first layer generating just one output, we can make several outputs. In our diagram, we'll add a second output, v sub 1, and we'll connect this to a third input into our second layer, x sub 2. Keep in mind that the x sub 0 input to every layer will always be equal to 1. That bias node shows up again in every layer. Now there are two nodes, shared by both layers. We can modify our equations accordingly to specify which of the shared nodes we are talking about. They behave exactly the same, so we can be efficient and reuse our equation, but we can specify subscript j to indicate which output we're talking about. So now if I'm connecting the ith input to the jth output, then I and j will determine which weight is applied and which u's get added together to create the output v sub j. And we can do this as many times as we want. We can add as many of these shared nodes as we care to. The model as a whole only knows about the input, x sub 1, into the first layer, and the output, v sub 0, of the last layer. From the point of view of someone sitting outside the model, the shared nodes between layer 1 and layer 2 are hidden. They're inside the black box. Because of this, they're called hidden nodes. We can take this two-layer linear network, create 100 hidden nodes, set all of the weights randomly, and see what model it produces. Even after adding all of this structure, the resulting models are still straight lines. In fact, it doesn't matter how many layers you have or how many hidden nodes each layer has, any combination of these linear elements with weights and sums will always produce a straight line result. This is actually one of the traits of linear computation that makes it so easy to work with. But unfortunately for us, it also makes really boring models. Sometimes a straight line is good enough, but that's not why we go to neural networks. We're going to want something a little more sophisticated. In order to get more flexible models, we're going to need to add some nonlinearity. We'll modify our linear equation here. After we calculate our output, v sub 0, we subject it to another function, f, which is not linear, and we'll call the result y sub 0. One really common nonlinear function to add here is the logistic function. It's shaped like an S, so sometimes it's called a sigmoid function too. Although that can be confusing because technically any function shaped like an S is a sigmoid. We can get a sense of what logistic functions look like by choosing random weights for this one input, one output, one layer network, and meeting the family. One notable characteristic of logistic functions is that they live between 0 and 1. For this reason, they're also called squashing functions. You can imagine taking a straight line and then squashing the edges and bending and hammering it down so that the whole thing fits between 0 and 1, no matter how far out you go. Working with logistic functions brings us to another connection with machine learning models, logistic regression. This is a bit confusing because regression refers to finding a relationship between an input and an output, usually in the form of a line or a curve or a surface of some type. Logistic regression is actually used as a classifier most of the time. It finds a relationship between a continuous input variable and a categorical output variable. It treats observations of one category as zeros, treats observations of the other category as ones, and then finds the logistic function that best fits all those observations. Then to interpret the model, we add a threshold, often around 0.5, and wherever the curve crosses the threshold, there's a demarcation line. Everything to the left of that line is predicted to fall into one category, and everything to the right of that line is predicted to fall into the other. This is how a regression algorithm gets modified to become a classification algorithm. As with linear functions, there's no reason not to add more inputs. We know that logistic regression can work with many input variables, and we can represent that in our graph as well. Here, we just add one in order to keep the plot three-dimensional, but we could add as many as we want. To see what type of functions this network can create, we can choose a bunch of random values for the weights. As you might have expected, the functions we create are still S-shaped, but now they're three-dimensional. They look like a tablecloth laid across two tables of unequal height. More importantly, if you look at the contour lines projected down onto the floor of the plot, you can see that they are all perfectly straight. The result of this is that any threshold we choose for doing classification will split our input space up into two halves, with the divider being a straight line. This is why logistic regression is described as a linear classifier. Whatever the number of inputs you have, whatever dimensional space you're working in, logistic regression will always split it into two halves using a line or a plane or a hyperplane of the appropriate dimensions. Another popular nonlinear function is the hyperbolic tangent. It's closely related to the logistic function and can be written in a very symmetric way. We can see when we choose some random weights and look at examples that hyperbolic tangent curves look just like logistic curves, except that they vary between -1 and +1. Just like we tried to do before with linear functions, we can use the output of one layer as the input to another layer. We can stack them in this way and can even add hidden nodes the same way we did before. Here we just show two hidden nodes in order to keep the diagram simple, but you can imagine as many as you want there. When we choose random weights for this network and look at the output, we find that things get interesting. We've left the realm of the linear. Because the hyperbolic tangent function is nonlinear, when we add them together, we get something that doesn't necessarily look like a hyperbolic tangent. We get curves, wiggles, peaks, and valleys, and a much wider variety of behavior than we ever saw with single layer networks. We can take the next step and add another layer to our network. Now we have a set of hidden nodes between layer 1 and layer 2, and another set of hidden nodes between layer 2 and layer 3. Again, we choose random values for all the weights and look at the types of curves it can produce. Again, we see wiggles and peaks, valleys, and a wide selection of shapes. If it's hard to tell the difference between these curves and the curves generated by a two-layer network, that's because they're mathematically identical. We won't try to prove it here, but there's a cool result that shows that any curve you can create using a many-layered network, you can also create using a two-layer network, as long as you have enough hidden nodes. The advantage of having a many-layered network is that it can help you create more complex curves using fewer total nodes. For instance, in our two-layer network, we used 100 hidden nodes. But in our three-layer network, we used 11 hidden nodes in the first layer and 9 hidden nodes in the second layer. That's only a fifth of the total number we used in our two-layer network, but the curves it produces show similar richness. We can use these fancy wiggly lines to make a classifier, as we did with logistic regression. Here we use the zero line as the cutoff. Everywhere that our curve crosses the zero line, there's a divider. In every region that the curve sits above the zero line, we'll call this category A. And similarly, everywhere the curve is below the zero line, we have category B. What distinguishes these nonlinear classifiers from linear ones is that they don't just split the space into two halves. In this example, regions of A and B are interleaved. Building a classifier around a multi-layer nonlinear network gives it a lot more flexibility. It can learn more complex relations. This particular combination of multi-layer network with hyperbolic tangent nonlinear function has its own name, a multi-layer perceptron. As you can guess, when you have only one layer, it's just called a perceptron. And in that case, you don't even need to add the nonlinear function to make it work. The function will still cross the x-axis at all the same places. Here is the full network diagram of a multi-layer perceptron. This representation is helpful because it makes every single operation explicit. However, it's also visually cluttered and it's difficult to work with. Because of this, it's most often simplified to look like circles connected by lines. This implies all the operations we saw in the previous diagram. Connecting lines each have a weight associated with them. Hidden nodes and output nodes perform summation and nonlinear squashing. But in this diagram, all of that is implied. In fact, our bias nodes, the nodes that always have a value of 1 in each layer, are omitted for clarity. So our original network reduces to this. The bias nodes are still present and their operation hasn't changed at all, but we leave them out to make a cleaner picture. We only show 2 hidden nodes from each layer here, but in practice we used quite a few more. Again, to make the diagram as clean as possible, we often don't show all the hidden nodes. We just show a few, and the rest are implied. Here's a generic diagram then for a 3-layer, single input, single output network. Notice that if we specify the number of inputs, the number of outputs, and the number of layers, and the number of hidden nodes in each layer, then we can fully define a neural network. We can also take a look at a 2-input, single output neural network. Because it has 2 inputs, when we plot its outputs, it'll be a 3-dimensional curve. We can once again choose random weights and generate curves to see what types of functions this neural network might be able to represent. This is where it gets really fun. With multiple inputs, multiple layers, and nonlinear activation functions, neural networks can make really crazy shapes. It's almost correct to say that they could make any shape you want. It's worth taking a moment, though, to notice what its limitations are. First, notice that all of the functions fall between plus and minus 1. The dark red and the dark green regions kiss the floor and the ceiling of this range, but they never cross it. This neural network would not be able to fit a function that extended outside of this range. Also, notice that these functions all tend to be smooth. They have hills and dips and valleys and wiggles and even points and wells, but it all happens relatively smoothly. If we hope to fit a function with a lot of jagged jumps and drops, this neural network might not be able to do a very good job of it. However, aside from these two limitations, the variety of functions that this neural network can produce is a little mind-boggling. We modified a single output neural network to be a classifier when we looked at the multilayer perceptron. Now there's another way to do this. We can use a two-output neural network instead. Outputs of a three-layer, one input, two output neural network like this, we can see that there are many cases where the two curves cross, and in some instances, they cross in several places. We can use this to make a classifier. Wherever the one output is greater than another, it can signify that one category dominates another. Graphically, wherever the two output functions cross, we can draw a vertical line. This chops up the input space into regions. In each region, one output is greater than the other. For instance, wherever the blue line is greater, we can assign that to be category A. Then wherever the peach-colored line is greater, those regions are category B. Just like the multilayer perceptron, this lets us chop the space up in more complex ways than a linear classifier could. Regions of category A and category B can be shuffled together arbitrarily. When you only have two outputs, the advantages of doing it this way over a multilayer perceptron with just one output are not at all clear. However, if you move to three or more outputs, the story changes. Now, we have three separate outputs and three separate output functions. We can use our same criterion of letting the function with the maximum value determine the category. We start by chopping up the input space according to which function has the highest value. Each function represents one of our categories. We're going to assign our first function to be category A and label every region where it's on top as category A. Then we can do the same with our second function and our third. Using this trick, we're no longer limited to two categories. We can create as many output nodes as we want and learn and chop up the input space into that many categories. It's worth pointing out that the winning category may not be the best by very much. In some cases, you can see they can be very close. One category will be declared the winner, but the next runner-up may be almost as good a fit. There's no reason that we can't extend this approach to two or more inputs. Unfortunately, it does get harder to visualize. You have to imagine several of these lumpy landscape plots on top of each other. And in some regions, one will be greater than the others. In that region, that category associated with that output will be dominant. To get a qualitative sense for what these regions might look like, you can look at the projected contours on the floor of these plots. In the case of a multilayer perceptron, these plots are all sliced at the y equals 0 level. That means if you look at the floor of the plot, everything in any shade of green will be one category, and everything in any shade of red will be the other category. The first thing that jumps out about these category boundaries is how diverse they are. Some of them are nearly straight lines, albeit with a small wiggle. Some of them have wilder bends and curves. And some of them chop the input space up into several disconnected regions of green and red. Sometimes there's a small island of green or island of red in the middle of a sea of the other color. The variety of boundaries is what makes this such a powerful classification tool. The one limitation we can see looking at it this way is that the boundaries are all smoothly curved. Sometimes those curves are quite sharp, but usually they're gentle and rounded. This shows the natural preference that neural networks with hyperbolic tangent activation functions have for smooth functions and smooth boundaries. The goal of this exploration was to get an intuitive sense for what types of functions and category boundaries neural networks can learn when used for regression or classification. We've seen both their power and their distinct preference for smoothness. We've only looked at two nonlinear activation functions, logistic and hyperbolic tangent, both of which are very closely related. There are lots of others, and some of them do a bit better at capturing sharp nonlinearities. Rectified linear units, or ReLUs, for instance, produce surfaces and boundaries that are quite a bit sharper. But my hope was to seed your intuition with some examples of what's actually going on under the hood when you train your neural network. Here are the most important things to walk away with. Neural networks learn functions and can be used for regression. Some activation functions limit the output range, but as long as that matches the expected range of your outputs, it's not a problem. Second, neural networks are most often used for classification. They've proven pretty good at it. Third, neural networks tend to create smooth functions when used for regression, and smooth category boundaries when used for classification. Fourth, for fully connected vanilla neural networks, a two-layer network can learn any function that a deep network can learn. However, a deep network might be able to learn it with fewer nodes. Fifth, making sure that inputs are normalized, that is, they have a mean near zero and a standard deviation of less than 1. This helps neural networks to be more sensitive to their relationships. I hope this helps you as you jump into your next project. Happy building.
Welcome to How Convolutional Neural Networks Work. Convolutional neural networks, or ConvNets or CNNs, can do some pretty cool things. If you feed them a bunch of pictures of faces, for instance, they'll learn some basic things like edges and dots, bright spots, dark spots. And then because they're a multi-layer neural network, that's what gets learned in the first layer. The second layer are things that are recognizable as eyes, noses, mouths. And the third layer are things that look like faces. Similarly, if you feed it a bunch of images of cars, down at the lowest layer, you'll get things, again, that look like edges. And then higher up, you get things that look like tires and wheel wells and hoods. And at a level above that, things that are clearly identifiable as cars. CNNs can even learn to play video games by forming patterns of the pixels as they appear on the screen and learning what is the best action to take when it sees a certain pattern. A CNN can learn to play video games, in some cases, far better than a human ever could. Not only that, if you take a couple of CNNs and have them set to watching YouTube videos, one can learn objects by, again, picking out patterns, and the other one can learn types of grasps. This then, coupled with some other execution software, can let a robot learn to cook just by watching YouTube. So there's no doubt CNNs are powerful. Usually when we talk about them, we do so in the same way we might talk about magic. But they're not magic. What they do is based on some pretty basic ideas applied in a clever way. So to illustrate these, we'll talk about a very simple toy convolutional neural network. What this one does is takes in an image, a two-dimensional array of pixels. You can think of it as a checkerboard, and each square on the checkerboard is either light or dark. And then by looking at that, the CNN decides whether it's a picture of an X or of an O. So for instance, on top there, we see an image with an X drawn in white pixels on a black background. And we would like to identify this as an X. And the O, we'd like to identify as an O. So how a CNN does this is has several steps in it. What makes it tricky is that the X is not exactly the same every time. The X or the O can be shifted, it can be bigger or smaller, it can be rotated a little bit, thicker or thinner, and in every case we would still like to identify whether it's an X or an O. Now the reason that this is challenging is because for us, deciding whether these two things are similar is straightforward. We don't even have to think about it. For a computer, it's very hard. What a computer sees is this checkerboard, this two-dimensional array, as a bunch of numbers, ones and minus ones. A 1 is a bright pixel, a -1 is a black pixel, and what it can do is go through pixel by pixel and compare whether they match or not. So to a computer, it looks like there are a lot of pixels that match, but some that don't, quite a few that don't actually. And so it might look at this and say, I'm really not sure whether these are the same. And so it would, because a computer is so literal, it would say, uncertain. I can't say that they're equal. Now, one of the tricks that convolutional neural networks use is to match parts of the image rather than the whole thing. So if you break it down into its smaller parts or features, then it becomes much more clear whether these two things are similar. So examples of these little features are little mini images. In this case, just 3 pixels by 3 pixels. The one on the left is a diagonal line slanting downward from left to right. The one on the right is also a diagonal line slanting in the other direction. And the one in the middle is a little X. These are little pieces of the bigger image. And you can see as we go through, if you choose the right feature and put it in the right place, it matches the image exactly. So, okay, we have the bits and pieces. Now, to take a step deeper, the math behind matching these is called filtering. And the way this is done is a feature is lined up with the little patch of the image, and then one by one, the pixels are compared. They're multiplied by each other, and then added up and divided by the total number of pixels. So to step through this, to see why it makes sense to do this, you can see starting in the upper left-hand pixel in both the feature and the image patch, multiplying a 1 by a 1 gives you a 1. And we can keep track of that by putting that in the position of the pixel that we're comparing. We step to the next one, -1 times -1 is also a 1. And we continue to step through, pixel by pixel, multiplying them all by each other, and because they're always the same, the answer is always 1. When we're done, we take all these 1s and add them up and divide by 9, and the answer is 1. So now we want to keep track of where that feature was in the image, and we put a 1 there. Say, when we put the feature here, we get a match of 1. That is filtering. Now we can take that same feature and move it to another position and perform the filtering again. And we start with the same pattern. The first pixel matches, the second pixel matches. The third pixel does not match. -1 times 1 equals -1. So we record that in our results. And we go through and do that through the rest of the image patch. And when we're done, we notice we have 2 -1s this time. So we add up all the pixels, which add up to 5, divide by 9, and we get a 0.55. So this is very different than our 1. And we can record the 0.55 in that position, where we were, where it occurred. So by moving our filter around to different places in the image, we actually find different values for how well that filter matches or how well that feature is represented at that position. So this becomes a map of where the feature occurs. By moving it around to every possible position, we do convolution. That's just the repeated application of this feature, this filter, over and over again. And what we get is a nice map across the whole image of where this feature occurs. And if we look at it, it makes sense. This feature is a diagonal line slanting downward, left to right, which matches the downward left to right diagonal of the X. So if we look at our filtered image, we see that all of the high numbers, 1s and 0.77s, are all right along that diagonal. That suggests that that feature matches along that diagonal much better than it does elsewhere in the image. To use a shorthand notation here, we'll do a little X with a circle in it to represent convolution, the act of trying every possible match. And we repeat that with other features. We can repeat that with our X filter in the middle and with our upward slanting diagonal line in the bottom. And in each case, the map that we get of where that feature occurs is consistent with what we would expect based on what we know about the X and about where our features match. This act of convolving an image with a bunch of filters, a bunch of features, and creating a stack of filtered images is we'll call a convolution layer. A layer because it's an operation that we can stack with others, as we'll show in a minute. In convolution, one image becomes a stack of filtered images. We get as many filtered images out as we have filters. So, convolution layer is one trick that we have. The next big trick that we have is called pooling. This is how we shrink the image stack. And this is pretty straightforward. We start with the window size, usually 2 by 2 pixels or 3 by 3 pixels, and a stride, usually 2 pixels. Just in practice, these work best. And then we take that window and walk it in strides across each of the filtered images. From each window, we take the maximum value. So to illustrate this, we start with our first filtered image. We have our 2 pixel by 2 pixel window. Within that pixel, the maximum value is 1. So we track that and then move to our stride of 2 pixels. We move 2 pixels to the right and repeat. Out of that window, the maximum value is 0.33, etc., 0.55. And when we get to the end, we have to be creative. We don't have all the pixels representative, so we take the max of what's there. And we continue doing this across the whole image. And when we're done, what we end up with is a similar pattern, but smaller. We can still see our high values are all on the diagonal. But instead of 7 by 7 pixels in our filtered image, we have a 4 by 4 pixel image. So it's half as big as it was about. This makes a lot of sense to do if you can imagine if instead of starting with a 9 by 9 pixel image, we had started with a 9,000 by 9,000 pixel image. Shrinking it is convenient for working with it. Makes it smaller. The other thing it does is pooling doesn't care where in that window that maximum value occurs. So that makes it a little less sensitive to position. And the way this plays out is that if you're looking for a particular feature in an image, it can be a little to the left, a little to the right, maybe a little rotated, and it'll still get picked up. So we do max pooling with all of our stack of filtered images and get, in every case, smaller set of filtered images. Now, that's our second trick. Third trick, normalization. This is just a step to keep the math from blowing up and keep it from going to 0. All you do here is everywhere in your image that there is a negative value, change it to 0. So for instance, if we're looking back at our filtered image, we have these what are called rectified linear units. That's the little computational unit that does this. But all it does is steps through everywhere there's a negative value, change it to 0. Another negative value, change it to 0. By the time you're done, you have a very similar looking image, except there's no negative values. They're just zeros. And we do this with all of our images, and this becomes another type of layer. So in a rectified linear unit layer, a stack of images becomes a stack of images with no negative values. Now, what's really fun, the magic starts to happen here when we take these layers, convolution layers, rectified linear unit layers, and pooling layers, and we stack them up so that the output of one becomes the input of the next. You'll notice that what goes into each of these and what comes out of these looks like an array of pixels, or an array of pixels. And because of that, we can stack them nicely. We can use the output of one for the input of the next. And by stacking them, we get these operations building on top of each other. What's more, we can repeat the stacks. We can do deep stacking. You can imagine making a sandwich that is not just one patty and one slice of cheese and one lettuce and one tomato, but a whole bunch of layers, double, triple, quadruple deckers, as many times as you want. Each time, the image gets more filtered as it goes through convolution layers, and it gets smaller as it goes through pooling layers. Now, the final layer in our toolbox is called a fully connected layer. Here, every value gets a vote on what the answer is going to be. So we take our now much filtered and much reduced in size stack of images. We break them out, we just rearrange and put them into a single list because it's easier to visualize that way. And then each of those connects to one of our answers that we're going to vote for. When we feed this an X, there will be certain values here that tend to be high. They tend to predict very strongly that this is going to be an X. They get a lot of vote for the X outcome. Similarly, when we feed in a picture of an O to our convolutional neural network, there are certain values here at the end that tend to be very high and tend to predict strongly when we're going to have an O at the end. So they get a lot of weight, a strong vote for the O category. Now when we get a new input and we don't know what it is and we want to decide, the way this works is the input goes through all of our convolutional, our rectified linear unit, our pooling layers, and comes out to the end here. We get a series of votes, and then based on the weights that each value gets to vote with, we get a nice average vote at the end. In this case, this particular set of inputs votes for an X with a strength of 0.92 and an O with a strength of 0.51. So here, definitely X is the winner, and so the neural network would categorize this input as an X. So in a fully connected layer, a list of feature values becomes a list of votes. Now, again, what's cool here is that a list of votes looks a whole lot like a list of feature values, so you can use the output of one for the input of the next. And so you can have intermediate categories that aren't your final votes, or sometimes these are called hidden units in a neural network. And you can stack as many of these together as you want also. But in the end, they all end up voting for an X or an O, and whoever gets the most votes wins. So if we put this all together, then a two-dimensional array of pixels in results in a set of votes for a category out at the far end. So there are some things that we have glossed over here. You might be asking yourself where all of the magic numbers come from. Things that I pulled out of thin air include the features in the convolutional layers, those convenient 3 pixel by 3 pixel diagonal lines at the X. Also, the voting weights in the fully connected layers. I really waved my hands about how those are obtained. In all these cases, the answer is the same. There is a trick called backpropagation. All of these are learned. You don't have to know them. You don't have to guess them. The deep neural network does this on its own. So the underlying principle behind backpropagation is that the error in the final answer is used to determine how much the network adjusts and changes. So in this case, if we knew we were putting in an X, and we got a 0.92 vote for an X, and that would be an error of 0.08, and we got a 0.51 vote for an O, we know that that would be an error of 0.49, actually an error of 0.51 because it should be 0. Then if we add all that up, we get an error of what should be 0.59. So what happens with this error signal is it helps drive a process called gradient descent. If there is another bit of something that is pretty special sauce to deep neural networks, it is the ability to do gradient descent. So for each of these magic numbers, each of the feature pixels, each voting weight, they're adjusted up and down by a very small amount to see how the error changes. The amount that they're adjusted is determined by how big the error is. Large error, they're adjusted a lot. Small error, just a tiny bit. No error, they're not adjusted at all. You have the right answer, stop messing with it. As they're adjusted, you can think of that as sliding a ball slightly to the left and slightly to the right on a hill. You want to find the direction where it goes downhill. You want to go down that slope, down that gradient to find the very bottom, because the bottom is where you have the very least error. That's your happy place. So after sliding it to the left and to the right, you find the downhill direction and you leave it there. Doing that many times over lots of iterations, lots of steps, helps all of these values across all the features and all of the weights settle in to what's called a minimum. And at that point, the network is performing as well as it possibly can. If it adjusts any of those a little bit, its error will go up. Now, there are some things called hyperparameters, and these are knobs that the designer gets to turn, decisions the designer gets to make. These are not learned automatically. In convolution, figuring out how many features should be used, how big those features should be, how many pixels on a side. In the pooling layers, choosing the window size and the window stride. And in fully connected layers, choosing the number of hidden neurons, intermediate neurons. All of these things are decisions that the designer gets to make. Right now, there are some common practices that tend to work better than others, but there is no principled way. There's no hard and fast rules for the right way to do this. And in fact, a lot of the advances in convolutional neural networks are in getting combinations of these that work really well. Now, in addition to this, there are other decisions the designer gets to make, like how many of each type of layer and in what order. And for those that really like to go off the rails, can we design new types of layers entirely and slip them in there and get new fun behaviors? These are all things that people are playing with to try to eke out more performance and address stickier problems with CNNs. Now, what's really cool about these, we've been talking about images, but you can use any two-dimensional, or even for that matter, 3- or 4-dimensional data. But what's important is that in your data, things closer together are more closely related than things far away. What I mean by that is, if you look at an image, 2 rows of pixels or 2 columns of pixels are right next to each other, they're more closely related than rows or columns that are far away. Now, what you can do is you can take something like sound and you can chop it up into little time steps. And for each piece of time, the time step right before it and right after is more closely related than time steps that are far away. And the order matters. You can also chop it up into different frequency bands. Bass, mid-range, treble. You can slice it a whole lot more finely than that. And again, those frequency bands are the ones closer together, are more closely related, and you can't rearrange them. The order matters. Once you do this with sound, it looks like a picture. It looks like an image, and you can use convolutional neural networks with them. You can do something similar with text, where the position in the sentence becomes the column, and the row is words in a dictionary. In this case, it's hard to argue whether order matters, that order matters. It's hard to argue that words in a dictionary are, that some are more closely related than others in all cases. And so the trick here is to take a window that spans the entire column, top to bottom, and then slide it left to right. That way it captures all of the words, but it only captures a few positions in the sentence at a time. Now, the other side of this limitation of convolutional neural networks is that they're really designed to capture local spatial patterns. Spatial in the sense of things that are next to each other matter quite a bit. So if the data can't be made to look like an image, then they're not as useful. So an example of this is, say, some customer data. If I have each row, it's a separate customer. Each column is a separate piece of information about that customer, such as their name, their address, what they bought, what websites they visited. Then this doesn't so much look like a picture. I can take and rearrange those columns and rearrange those rows, and this still means the same thing. It's still equally easy to interpret. If I were to take an image and rearrange the columns and rearrange the rows, it would result in a scramble of pixels, and it would be difficult or impossible to say what the image was of. There I would lose a lot of information. So as a rule of thumb, if your data is just as useful after swapping out any of the columns for each other, then you can't use convolutional neural networks. So the take home is that convolutional neural networks are great at finding patterns and using them to classify images. If you can make your problem look like finding cats on the internet, then they're a huge asset. Applications of machine learning have gotten a lot of traction in the last few years. There's a couple of big categories that have had wins. One is identifying pictures, the equivalent of finding cats on the internet, and any problem that can be made to look like that. And the other is sequence-to-sequence translation. This can be speech to text or one language to another. Most of the former are done with convolutional neural networks. Most of the latter are done with recurrent neural networks, particularly long short-term memory. To give an example of how long short-term memory works, we will consider the question of what's for dinner. Let's say for a minute that you are a very lucky apartment dweller and you have a flatmate who loves to cook dinner. Every night he cooks one of three things: sushi, waffles, or pizza. And you would like to be able to predict what you're going to have on a given night, so you can plan the rest of your days eating accordingly. In order to predict what you're going to have for dinner, you set up a neural network. The inputs to this neural network are a bunch of items like the day of the week, the month of the year, whether or not your flatmate was in a late meeting, variables that might reasonably affect what you're going to have for dinner. Now, if you're new to neural networks, I highly recommend you take a minute and stop to watch the How Neural Networks Work tutorial. There's a link down in the comments section. If you'd rather not do that right now, and you're still not familiar with neural networks, you can think of them as a voting process. And so in the neural network that you set up, there's a complicated voting process, and all of the inputs like day of the week and month of the year go into it, and then you train it on your history of what you've had for dinner, and you learn how to predict what's going to be for dinner tonight. The trouble is that your network doesn't work very well. Despite carefully choosing your inputs and training it thoroughly, you still can't get much better than chance predictions on dinner. As is often the case with complicated machine learning problems, it's useful to take a step back and just look at the data. And when you do that, you notice a pattern. Your flatmate makes pizza, then sushi, then waffles, then pizza again in a cycle. It doesn't depend on the day of the week or anything else. It's in a regular cycle. So knowing this, we can make a new neural network. In our new one, the only inputs that matter are what we had for dinner yesterday. So if we know if we had pizza for dinner yesterday, it'll be sushi tonight, sushi yesterday, waffles tonight, and waffles yesterday, pizza tonight. It becomes a very simple voting process, and it's right all the time because your flatmate is incredibly consistent. Now, if you happen to be gone on a given night, let's say yesterday you were out, you don't know what was for dinner yesterday. You can still predict what's going to be for dinner tonight by thinking back 2 days ago. Think, what was for dinner then? So what would be predicted for you last night? And then you can use that prediction in turn to make a prediction for tonight. So we make use of not only our actual information from yesterday, but also what our prediction was yesterday. So at this point, it's helpful to take a little detour and talk about vectors. A vector is just a fancy word for a list of numbers. If I wanted to describe the weather to you for a given day, I could say the high is 76 degrees Fahrenheit, the low is 43, the wind's 13 miles an hour, there's going to be a 1/4 inch of rain, and the relative humidity is 83%. That's all a vector is. The reason that it's useful is vectors, lists of numbers, are computers' native language. If you want to get something into a format that it's natural for a computer to compute, to do operations on, to do statistical machine learning, lists of numbers are the way to go. Everything gets reduced to a list of numbers before it goes through an algorithm. We can also have a vector for statements like, it's Tuesday. In order to encode this kind of information, what we do is we make a list of all the possible values it could have, in this case, all the days of the week, and we assign a number to each. And then we go through and set them all equal to 0, except for the one that is true right now. This format is called one-hot encoding, and it's very common to see a long vector of zeros with just one element being 1. It seems inefficient, but for a computer, this is a lot easier way to ingest that information. So we can make a one-hot vector for our prediction for dinner tonight. We set everything equal to 0 except for the dinner item that we predict. So in this case, we'll be predicting sushi. Now we can group together our inputs and outputs into vectors, separate lists of numbers. And it becomes a useful shorthand for describing this neural network. So we can have our dinner yesterday vector, our predictions for yesterday vector, and our prediction for today vector. And the neural network is just connections between every element in each of those input vectors to every element in the output vector. And to complete our picture, we can show how the prediction for today will get recycled. The dotted line there means hold on to it for a day and then reuse it tomorrow. And it becomes our yesterday's predictions tomorrow. Now we can see how if we were lacking some information, let's say we were out of town for 2 weeks, we can still make a good guess about what's going to be for dinner tonight. We just ignore the new information part and we can unwrap or unwind this vector in time until we do have some information to base it on, and then just play it forward. And when it's unwrapped, it looks like this. And we can go back as far as we need to and see what was for dinner and then just trace it forward and play out our menu over the last 2 weeks until we find out what's for dinner tonight. So this was a nice simple example that showed recurrent neural networks. Now to show how they don't meet all of our needs, we're going to write a children's book. It'll have sentences of the format, Doug saw Jane, period. Jane saw Spot, period. Spot saw Doug, period. And so on. So our dictionary is small, just the words Doug, Jane, Spot, saw, and a period. And the task of the neural network is to put these together in the right order to make a good children's book. So to do this, we replace our food vectors with our dictionary vectors. Here again, it's just a list of numbers representing each of the words. So for instance, if Doug was the most recent word that I saw, my new information vector would be all zeros except for a 1 in the Doug position.
And we similarly can represent our predictions and our predictions from yesterday. Now, after training this neural network and teaching it what to do, we would expect to see certain patterns. For instance, anytime a name comes up, Jane, Doug, or Spot, we would expect that to vote heavily for the word saw or for a period, because those are the two words in our dictionary that can follow a name. Similarly, if we had predicted a name on the previous time step, we would expect those to vote also for the word saw or for a period. And then by a similar method, anytime we come across the word saw or a period, we know that a name has to come after that. So it will learn to vote very strongly for a name, Jane, Doug, or Spot. So in this form, in this formulation, we have a recurrent neural network. For simplicity, I'll take the vectors and the weights and collapse them down to that little symbol with the dots and the arrows, the dots and the lines connecting them. And there's one more symbol we haven't talked about yet. This is a squashing function, and it just helps the network to behave. How it works is you take all of your votes coming out and you subject them to this squashing function. For instance, if something received a total vote of 0.5, you draw a vertical line up. Where it crosses the function, you draw a horizontal line over to the y-axis, and there's your squashed version out. For small numbers, the squashed version is pretty close to the original version, but as your number gets larger, the number that comes out is closer and closer to 1. And similarly, if you put in a big negative number, then what you'll get out will be very close to -1. No matter what you put in, what comes out is between -1 and 1. So this is really helpful when you have a loop like this, where the same values get processed again and again, day after day. It is possible, you can imagine if in the course of that processing, say something got voted for twice, it got multiplied by 2, in that case, it would get twice as big every time and very soon blow up to be astronomical. By ensuring that it's always less than 1, but more than -1, you can multiply it as many times as you want. You can go through that loop and it won't explode. In a feedback loop, this is an example of negative feedback or attenuating feedback. So you may have noticed our neural network in its current state is subject to some mistakes. We could get a sentence, for instance, of the form, Doug saw Doug, period. Because Doug strongly votes for the word saw, which in turn strongly votes for a name, any name, which could be Doug. Similarly, we could get something like Doug saw Jane, saw Spot, saw Doug. Because each of our predictions only looks back one time step, it has very short-term memory, then it doesn't use the information from further back, and it's subject to these types of mistakes. In order to overcome this, we take our recurrent neural network and we expand it, and we add some more pieces to it. The critical part that we add to the middle here is memory. We want to be able to remember what happened many time steps ago. So in order to explain how this works, I'll have to describe a few new symbols that we've introduced here. One is another squashing function, this one with a flat bottom. One is an X in a circle, and one is a cross in a circle. So the cross in a circle is element by element addition. The way it works is you start with two vectors of equal size, and you go down each one. You add the first element of one vector to the first element of another vector, and then the total goes into the first element of the output vector. So 3 plus 6 equals 9. And then you go to the next element. 4 plus 7 equals 11. And so your output vector is the same size of each of your input vectors. Just a list of numbers, same length, but it's the sum, element by element, of the two. And very closely related to this, you've probably guessed, the X in the circle is element by element multiplication. It's just like addition, except instead of adding, you multiply. For instance, 3 times 6 gives you a first element of 18. 4 times 7 gets you 28. Again, the output vector is the same size of each of the input vectors. Now, element-wise multiplication lets you do something pretty cool. You imagine that you have a signal, and it's like a bunch of pipes. And they have a certain amount of water trying to flow down them. In this case, we'll just assign the number to that of 0.8. It's like a signal. Now, on each of those pipes, we have a faucet. And we can open it all the way, close it all the way, or keep it somewhere in the middle to either let that signal come through or block it. So in this case, an open gate, an open faucet would be a 1, and a closed faucet would be a 0. And the way this works with element-wise multiplication, we get 0.8 times 1 equals 0.8. That signal passed right through into the output vector. But the last element, 0.8 times 0 equals 0. That signal, the original signal, was effectively blocked. And then with the gating value of 0.5, the signal was passed through, but it's smaller. It's attenuated. So gating lets us control what passes through and what gets blocked, which is really useful. Now, in order to do gating, it's nice to have a value that you know is always between 0 and 1. So we introduce another squashing function. This will represent with a circle with a flat bottom, and it's called the logistic function. It's very similar to the other squashing function, the hyperbolic tangent, except that it just goes between 0 and 1 instead of -1 and 1. Now, when we introduce all of these together, what we still have the combination of our previous predictions and our new information. Those vectors get passed, and we make predictions based on them. Those predictions get passed through, but the other thing that happens is a copy of those predictions is held onto for the next time step, the next pass through the network. And some of them, here's a gate right here, some of them are forgotten, some of them are remembered. The ones that are remembered are added back into the prediction. So now we have not just prediction, but predictions plus the memories that we've accumulated and that we haven't chosen to forget yet. Now there's an entirely separate neural network here that learns when to forget what. Based on what we're seeing right now, what do we want to remember? What do we want to forget? So you can see this is powerful. This will let us hold on to things for as long as we want. Now you've probably noticed though, when we are combining our predictions with our memories, we may not necessarily want to release all of those memories out as new predictions each time. So we want a little filter to keep our memories inside and let our predictions get out. And we add another gate for that, to do selection. It has its own neural network, so its own voting process, so that our new information and our previous predictions can be used to vote on what all the gates should be, what should be kept internal, and what should be released as a prediction. We've also introduced another squashing function here. Since we do an addition here, it's possible that things could become greater than 1 or smaller than -1, so we just squash it to be careful, to make sure it never gets out of control. And now, when we bring in new predictions, we make a lot of possibilities, and then we collect those with memory over time, and of all of those possible predictions, at each time step, we select just a few to release as the prediction for that moment. Each of these things, when to forget and when to let things out of our memory, are learned by their own neural networks. And the only other piece we need to add to complete our picture here is yet another set of gates. This lets us actually ignore possible predictions, possibilities as they come in. This is an attention mechanism. It lets things that aren't immediately relevant be set aside so they don't cloud the predictions in memory going forward. It has its own neural network and its own logistic squashing function and its own gating activity right here. Now, long short-term memory has a lot of pieces, a lot of bits that work together. And it's a little much to wrap your head around it all at once. So what we'll do is take a very simple example and step through it just to illustrate how a couple of these pieces work. It's admittedly an overly simplistic example, and feel free to poke holes at it later. When you get to that point, then you know you're ready to move on to the next level of material. So we are now in the process of writing our children's book. And for the purposes of demonstration, we'll assume that this LSTM has been trained on our children's books, examples that we want to mimic. And all of the appropriate votes and weights in those neural networks have been learned. Now we'll show it in action. So far, our story so far is Jane saw Spot, period. Doug is the most recent word that's occurred in our story. And also, not surprisingly for this time step, the names Doug, Jane, and Spot were all predicted as viable options. This makes sense. We had just wrapped up a sentence with a period. The new sentence can start with any name, so these are all great predictions. So we have our new information, which is the word Doug. We have our recent prediction, which is Doug, Jane, and Spot. And we pass these two vectors together to all four of our neural networks, which are learning to make predictions, to do ignoring, to do forgetting, and to do selection. So the first one of these makes some predictions. Given that the word Doug just occurred, this has learned that the word saw is a great guess to make for a next word. But it's also learned that having seen the word Doug, that it should not see the word Doug again very soon, seeing the word Doug at the beginning of a sentence. So it makes a positive prediction for saw and a negative prediction for Doug. It says, I do not expect to see Doug in the near future. So that's why Doug is in black. So this example is so simple we don't need to focus on attention or ignoring, so we'll skip over it for now. And this prediction of saw, not Doug, is passed forward. And again, for the purposes of simplicity, let's say there's no memory at the moment. So saw and Doug get passed forward. And then the selection mechanism here has learned that when the most recent word was a name, then what comes next is either going to be the word saw or a period. So it blocks any other names from coming out. So the fact that there's a vote for not Doug gets blocked here, and the word saw gets sent out as the prediction for the next time step. So we take a step forward in time now. The word saw is our most recent word and our most recent prediction. They get passed forward to all of these neural networks, and we get a new set of predictions. Because the word saw just occurred, we now predict that the words Doug, Jane, or Spot might come next. We'll pass over ignoring and attention in this example, and we'll take those predictions forward. Now, the other thing that happened is our previous set of possibilities, the word saw and not Doug, that we were maintaining internally, get passed to a forgetting gate. Now, the forgetting gate says, hey, my last word that occurred was the word saw. Based on my past experience, then I can forget about, I know that it occurred. I can forget that it happened. But I want to keep any predictions having to do with names. So it forgets saw, holds on to the vote for not Doug, and now at this element by element addition, we have a positive vote for Doug, a negative vote for Doug, and so they cancel each other out. So now we just have votes for Jane and Spot. Those get passed forward. Our selection gate, it knows that the word saw just occurred, and based on experience, a name will happen next. And so it passes through these predictions for names, And for the next time step then, we get predictions of only Jane and Spot, not Doug. This avoids the Doug saw Doug period type of error and the other errors that we saw. What this shows is that long short-term memory can look back 2, 3, many time steps and use that information to make good predictions about what's going to happen next. Now, to be fair to vanilla recurrent neural networks, they can actually look back several time steps as well, but not very many. LSTM can look back many time steps and has shown that successfully. This is really useful in some surprisingly practical applications. If I have text in one language and I want to translate it to text to another language, LSTMs work very well. Even though translation is not a word-to-word process, it's a phrase-to-phrase, or even in some cases a sentence-to-sentence process, LSTMs are able to represent those grammar structures that are specific to each language. And what it looks like is that they find the higher level idea and translate it from one mode of expression to another, just using the bits and pieces that we just walked through. Another thing that they do well is translating speech to text. Speech is just some signals that vary in time. It takes them and uses that then to predict what text, what word is being spoken, and it can use the history, the recent history of words, to make a better guess for what's going to come next. LSTMs are a great fit for any information that's embedded in time. Audio, video. My favorite application of all, of course, is robotics. Robotics is nothing more than an agent taking in information from a set of sensors and then based on that information, making a decision and carrying out an action. It's inherently sequential, and actions taken now can influence what is sensed and what should be done many time steps down the line. If you're curious what LSTMs look like in math, this is it. This is lifted straight from the Wikipedia page. I won't step through it, but it's encouraging that something that looks so complex expressed mathematically actually makes a fairly straightforward picture and story. And if you'd like to dig into it more, I encourage you to go to the Wikipedia page. Also, there are a collection of really good tutorials and discussions, other ways of explaining LSTMs that you may find helpful as well. I'd also strongly encourage you to visit Andre Karpathy's blog post showing examples of what LSTMs can do in text.
You can be forgiven if, when reading on the internet, you can substitute magic for deep learning and it fits perfectly in all of the articles. It's hard to know what it can't do. We don't get to talk about that very much. So the goal of this talk is just to talk about it on a really simple nuts and bolts level. The summary, in case you want to take a nap, deep learning is not magic, but it's really good at finding patterns. So if this is our brain, this is deep learning. An owl can fly, a fighter jet can fly, but there are a whole lot of things that an owl can do. And arguably, it's a much more complex thing. Although what the fighter jet does, it does really, really well. So deep learning is the fighter jet. Highly specialized, highly engineered. We're today going to talk about the basics. The Wright brothers airplane. If you understand the principles that it works on, then it's easy to branch out into the finer engineering details. But there's a whole lot of things that go on in a fighter jet that we're not going to talk about in detail. But this is nice. We can talk about this at a comfortable level. This is a neuron. Like all neurons, it's got a big body in the middle, a long tail, and some arms that branch off. Here's an artist's conception of a neural network or a bunch of neurons. Again, big body, long tails, arms. This is an actual picture of neurons in some brain tissue. Here, the bodies look like dots or blobs. You can see long tails, some of which branch, and the arms are pretty much invisible. And again, picture of some brain tissue. Here, the neurons are small dots, and you can barely see any of the tails at all. This is just to give you a sense of how tightly these things are packed together and how many of them there are. Big numbers with lots of zeros. And the crazy part is that a lot of them are connected to many more of their neighbors. This is one of our very first pictures of a neuron. Santiago Ramon de Cajal found a stain that he could introduce into a cell, turn the whole thing dark under his 19th century light microscope, was able to see this and then draw it with a pen and paper. This is old school. What you see here, though, bodies, long tails, lots of arms. We're going to turn it upside down because that's how they're typically represented in neural networks. And these pieces actually have names. The bodies are called the soma, the long tails are called axons, and the arms are called dendrites. We're going to draw a cartoon version of them. This is what they look like in PowerPoint. Now, the way that neurons work is that a dendrite, you can think of it as feelers or whiskers, and they look for electrical activity. They pick it up and send it to the body. The soma takes this and adds it together and accumulates it, and then depending on how fast it's accumulating it, it will activate the axon and send that signal along down the tail. The more dendrite activity there is, the more axonal activity there is. And if you get all of the dendrites really firing, then that axon is just as active as it can possibly be. In a very simplistic way, a neuron adds things up. Now, a synapse is where the axon from one neuron touches the dendrite of another. That's an artist's conception of it. You can see in Ramon y Cajal's drawings these little nubs or buttons. They're actually called boutons on the dendrites. And these are sites where the axon of another neuron touches them. And so you can imagine there's a little connection there. We'll represent that connection by a circle. And the diameter of that circle is the strength of that connection. Big circle, strong connection. And it can connect strongly or weakly or somewhere in between. We can put a number on this connection between 0 and 1. So a medium connection, we'll call it a 0.6. When the axon of the input neuron, the upstream neuron, is active, then it activates the dendrite of the output neuron. It passes that on with a modest strength. If that connection is strong, then it passes the signal on very strongly. If that connection is a 1, then when the axon is active, the next dendrite is very active. Likewise, if that connection is very weak, say a 0.2, then when the axon is active, the dendrite of the output neuron is only weakly activated. No connection at all is a 0. Now, this starts to get interesting because many different input neurons can connect to the dendrites of a single output neuron. And each connection has its own strength. We can redraw this by taking out all of the parallel dendrites and just drawing each axon and the single dendrite that it connects to and the connection strength represented, like this with the dots. We can substitute in numbers for that, the weights, although most often, we can also substitute in line thicknesses to show how strongly these things are connected. Most of the time, neural networks are drawn like this. And this is what we have. We went from the super complex slice of brain tissue with many subtleties in its operation and interconnection to a nice circle stick diagram, where each one of those sticks represents a weight. In its current form, it can still do some pretty cool things. The input neurons can connect to many output neurons. So actually what you get here is many inputs, many outputs, and the connection between each is distinct and has its own weight. This is, it's good for making pretty pictures. It's also great for representing combinations of things. And the way this is done, let's say you have 5 inputs labeled A, B, C, D, E. In this case, this output neuron has a strong connection to A, C, and E, very weak connections to B and D. That means when the A, C, and E input neurons are active all together, that really strongly activates the output neuron. B and D don't matter because they only connect weakly. So a way to think about this output neuron is in terms of the inputs that strongly activate it. So we call this the ACE neuron. And here we have an atomic example of what happens here. This output neuron represents a combination of the input neurons. This is neural networks in a nutshell. You can do this with any kind of input. So you have a really low-tech 4-pixel camera. Each of those 4 inputs is one of the pixels. Upper left, upper right, or lower right. In this particular neural network, with strong connections to the upper left and upper right pixel, we have a neuron, an output neuron, that represents this bar in the top half of the image. So we can combine letters, we can combine pixels to make small images. If you're doing text processing, the input neurons can represent individual words. So in this case, we're pulling words out of text. This output neuron is strongly connected to the input neurons for eye and ball. So we can call it the eyeball neuron. Similarly, we can have a sunglasses neuron, and input neurons can connect to many outputs. We can have an eyeglasses neuron just as easily. So going a little deeper into this is a somewhat trivial example to show how these things work in practice. So there's a guy at the shawarma place and makes shawarma like nobody else. And so you want to make sure and go when he's working there. And taking a step back, we actually have some domain knowledge here. We know he's got 2 schedules. Working in the morning, off in the evening, and off in the morning, working in the evening. Now, if we were to instrument this with sensors, we would have the working in the morning, off in the morning, working in the evening, off in the evening, and it might be useful to represent his working patterns in terms of a couple of output neurons that combine those. So this is the network that we would expect to end up with. Working in the morning, off in the evening is one pattern. Off in the morning, working in the evening is the other pattern. And you can see based on their connection strengths how they combine those inputs. Here would be the weights associated with those. Now the question is, how do we learn this? If we have to go in and fill it all in by hand, we haven't learned anything. It's just a fancier way of programming. And a lot of hard work, especially if you're dealing with many millions of input neurons. So we want to learn this automatically. So to start with, might be a little counterintuitive, we create our neural network, we have our input neurons, all we choose is the number of output neurons. In this case, we'll choose 2 because we happen to know we're learning 2 patterns. And then we randomly assign weights. Randomly generate numbers for each of these. It's a neural network that's completely, you roll the dice, you throw the sticks, and whatever falls out, that's what you start with. And then we start to gather data. We go, stand on the other side of the street, and we observe that the shawarma guy on this particular day worked in the morning and then went home, did not work in the evening. That means this input is active. We'll say it's at a level 1. Off in the morning is at a level 0 because we didn't observe it. Working in the morning is at 0, and off in the evening is at a 1 because we observed that too. So the next step is, for each of the output neurons, we calculate the activity. So in this case, An appropriately simple way to do this is just take the average of the inputs. So here, this weight is 0.3 and this weight is 0.1. So the average of those is 0.2. These neurons don't contribute anything because those inputs aren't active. Similarly, we can take the weight between this input and that output, 0.8 and 0.4. The average of those is 0.6. The output neuron on the right has a higher activity. That's the one we care about. We ignore all the others. If there's a million others, we ignore the rest and focus on this one for this time step. First thing we figure out is how wrong is it? Well, if it was perfect, if our neural network was perfect, that would have an activity of 1. It would be perfectly aligned with our inputs. But it only has an activity of 0.6, so the error is 0.4. The bigger that error is, that's a signal for how much we need to adjust our weights. When that error gets very small, it means that the weights really represent what's going on, and we don't need to make any more changes. Now the trick here, gradient descent. If there is an element of magic in deep learning, it's gradient descent. What you do is you go through and adjust each of these weights all through. You adjust it a little bit up and a little bit down and see which way decreases the error. The idea, the concept in gradient descent is weight is a quantity that you can shift a little bit side to side. As you do, this error will change. You can think of it as taking this ball. If you shift it a little bit to the left, it has to climb the hill. If you shift it a little to the right, it has to fall down the hill. And you like the direction. You choose the direction in which it gets lower. You want to bring that error down as low as it can get. And you take small incremental steps to keep everything numerically stable. So we go through and we do these for all of the neurons, for all of the weights that attach input neurons to our output. And we find that, yes, we want to increase this one. Because these aren't active, we actually have a bias toward low weights, so it doesn't hurt to decrease these. So we'll go ahead and decrease that weight, and decrease that weight, and increase that one. When we do that, sure enough, our new activity is 7, and so our error went from a 0.4 to a 0.3. It's a little bit better at representing what we saw. So that was one data point. We go back and we do the same thing the next day. It just so happens that this day, he's off in the morning, working in the evening. We adjust the weights, and we do that day after day after day, and eventually the weights will stop changing, or they'll slow down changing quite a bit. They'll get stable, and we get the system of weights that we originally saw because we had knowledge of the problem. So this is the Wright brothers airplane version of how training by backpropagation using gradient descent works. Backpropagation is a very specific way to do this that is computationally cheap and slick and fast, and you get your jet engine instead of the flapping of wings. So this is the underlying mechanism by which it works. So what we just looked at was a single layer. We have inputs, we have outputs. Every output is a combination of things that were on the previous layer. Now there's no reason then that we can't turn around and take that output layer and make it inputs for the next layer. And do that again and again. If a network has more than 3 layers or so, we call it deep. Some have more than 12. In some recent research at Microsoft, there are deep neural networks with more than 1,000 layers. There's no theoretical reason to limit the number of layers that you have. It just depends on the specifics of your problem. Now, what does deep get you? Why is deep special? If your input neurons are, say, letters in the alphabet, your first layer outputs, this is a deep neural network with all of the connections omitted for clarity. So these are your inputs. This is your first layer of outputs. They're combinations of those letters. Each level you go up, you get combinations of what happened the level before. So by the time you get to your second level of outputs, you're getting perhaps words in the English language, if that's what you're training on. The layer above that, you get combinations of words, short phrases, and so forth. And you can do this as deep as you like. So there's a variety of things you can learn with deep neural networks. A very popular one is images. If you take as your inputs pixels and show, instead of looking at shawarma guy schedule, you're looking at individual pictures as your training data set. What you start to learn after a while is these little representations of short lines and dots and patches. These are the primitives of an image. If you train on image of faces, then your second layer outputs start to look like eyes and noses and mouths and chins, and your third layer outputs start to look clearly recognizable as faces. Similarly, if you train on automobiles, your second layer outputs start to look like wheels and doors and windows, and your third layer output look like automobiles. So that's pretty cool. We didn't have to go in and twiddle any of those weights. This just learned that from seeing a bunch of pictures. You can do it on color images too. Here's an output of some of the output neurons of an 8-layer neural network. And as you get deeper, you can see things that are clearly recognizable and quite complex. You get spiders and rocking chairs and sailing and ships and teddy bears. You can also plug information in about music artists. So here's some research where output neurons were learned based on information about artists, and then their representation was plotted based on how similar they were in those output neurons. And so we see things like Kelly Clarkson and Beyonce are similar over here, which is also not too far from Taylor Swift and Avril Lavigne. Whereas if we go up here, we get Weezer, Black Keys, Modest Mouse, Presidents of the United States of America, all in the same neighborhood. This is a network that didn't know anything, still doesn't know anything about music, but because of the data that it gets on the input neurons, it's able to group these things appropriately. It finds patterns and then finds things that most closely fits those patterns. Turns out you can take Atari 2600 games, take the pixel representations, feed those in as input neurons, learn some fun features, and then pair it with something else called reinforcement learning that learns appropriate actions. And when you do this, for a certain class of games, it can learn to play them far better than any human player ever has or is ever likely to. And it turns out that you can take a robot and let it watch YouTube videos about how to cook. And it uses a pair of deep neural networks, one to interpret the video, one to learn to understand its own movements, and then pairs that with some other execution software to cook based on the video representations that it's seen. So while it's not magic, it's pretty cool. You can do some stuff with it. So as you're going through reading literature, reading popular articles about this, you can kind of play bingo. There are some buzzwords, some popular algorithms. You can think of a lot of these as the model numbers for the various fighter jets that are out there. But when you see any of these terms, if you like, you can mentally do the substitution of deep learning and apply what you know about the Wright brothers airplane, and most of it will still be accurate. So the bottom line, it's good at learning patterns. It doesn't do anything, but it's pretty good at learning patterns.
I'm excited to get to talk about two of my favorite topics at once: machine intelligence and robots. They go together pretty well, but they're not the same thing. You can definitely have one without the other. First, some disclaimers. I'm not going to give you the answer to human-level intelligence. I would if I had it, but I don't. Next, these are my own personal opinions. They're definitely not those of any current or former employer, and they don't reflect those of many experts in the field. Take them with a huge grain of salt. If they are useful, you're welcome to them, and if they're not, please discard them. Also, this story that I'm going to tell you is not rigorous. It doesn't have any equations, it's conceptual, and I just intend it to start a discussion and foster ideas. Throughout this presentation, we'll be talking about intelligence. The working definition that I propose is that it's a combination of how much one can do and how well one can do it. Notionally, you could be extremely good at only one thing and not be that intelligent. Also, you could do many things, but do them all very poorly, and also not be that intelligent. Intelligence is the combination of being able to do many things and to do them well. This is a functional definition of intelligence. There are many other potential definitions. Some of them can be measured experimentally and some can't. This particular definition has the advantage that if we wanted to reduce it down to a measurable set of tasks, we could. Because it is, at least in theory, observable, this allows us to have a scientific discussion about machine-level intelligence. It lets us form hypotheses that we could potentially falsify, and it lets us compare the relative intelligence of two separate agents. In short, it's practical and useful. Undoubtedly, some will find it philosophically unsatisfying. That's a separate conversation, but one that I would be happy to have in another forum. Using fake math, we can say that intelligence equals performance times generality. It's only fake because we haven't defined performance or generality yet. But assuming we do, you can imagine plotting them and putting them on a set of axes, like this. Although we haven't defined it quantitatively for human performance, what I would like to propose is that human performance is the level at which a human expert can do something. This can be measured in lots of different ways. It can be error rates, or the time required to execute a task, the time required to learn a task, the number of demonstrations required before one learns a task, the amount of energy expended when one performs a task, the subjective judgment of performance from a panel of human judges, the speed that someone does something. There are many aspects of performance, and I'm not going to try and specify or quantify them all here. I only list them to illustrate that we are considering performance in a broad sense. We're considering performance in a broad sense rather than in a narrow machine learning accuracy leaderboard sense. If we consider human-level performance to be something of a baseline, we can place it on our x-axis and then chop up the rest of the axis in equal increments. We'll make this a logarithmic scale to enable us to compare a very wide range of performances. Equal steps along this axis represent equal multiplicative factors of change. Human-level generality is the set of all the tasks that humans can do and have undertaken. These include things like writing stories, cooking pies, building cities, gathering and transmitting information all around the world, and even exploring the origin of the universe. It's a very broad set of activities. We can represent human-level generality on the y-axis. Roughly, this is the set of all tasks that a human or group of humans can do. We'll make the y-axis logarithmic as well, so an equal interval is a factor of 10 in performance, either multiplied or divide, depending on whether you're moving up or down. So human intelligence can be notionally represented by the area that's entailed by this point. Just want to point out there's no reason to believe that machines might not exceed human performance in some areas. Humans have a number of limitations that are built into the way in which we've achieved our intelligence through evolution. Things that may have been very useful at one point or may be useful broadly, but now may not be useful in pushing the limits of intelligence. Things like limited attention, instinctive drives, how every part of us fatigues, and a host of cognitive biases, all of which put some distance between us and perfectly rational or perfectly efficient or optimal behavior. Machines, by comparison, have a more nurturing environment in which to take root. They don't have to evolve. We're trying everything we can to encourage them. Now you can imagine on the performance generality axis another agent that can do a much larger set of tasks than humans, although do them all more poorly than a human could. So it might look like this. The area under that triangle, the overall intelligence, would still be comparable to that of a human. So we would call that human level intelligence also. You can also imagine an agent who can do a subset of the tasks that humans do, but do them so very much better that the area under that rectangle is also about the same as a human's. So again, human level intelligence. Now, if we take the set of all of these agents that have about the same area under their intelligence rectangle, then we get this curve representing human level intelligence. Any agent who falls along that curve would be comparable to a human. Any agent down and to the left of it, subhuman intelligence, and any agent up and to the right, superhuman intelligence. Now let's look at a few agents that you might be familiar with and see where they fall in this scheme. Chess-playing computers have been around for going on 30 years now. I should say world champion chess-playing computers have been around for almost 30 years. IBM's Deep Blue beat Garry Kasparov in 1989. This was a task that people assumed computers would have a very tough time with. It involved planning, strategy, thinking, mental models of your opponent. It seemed to take in the very peak of human cognition, and it seemed unlikely that such a thing could be done by a fancy calculator. But it did, and now a chess program running on your phone can do about the same as Deep Blue did. The current state of the art is a program called Stockfish, which has an ELO rating, which is like a chess skill score, of 3447. Compare this to the top-rated human player of all time, Magnus Carlsen, who achieved a 2882. The program and the human are not even comparable. They're not even close. It's worth noting that Stockfish is an open source project with code freely available and has a number of contributors scattered around the globe. Now, in terms of generality, Stockfish understands the rules of chess, and in fact, it understands them very well. It has a bunch of hints and tips and tricks built in by humans that are specific to chess. It uses a point system to evaluate pieces based on where they are and what the stage of the game is. It uses a full table of endgames. Once there are just a few pieces left on the board, the number of possibilities for how the game will play out are few enough that they can be completely enumerated. So there's no search, there's no solving, there's just essentially looking up in a giant table and figuring out what to do next. There are hand-tuned strategies for each phase of the game, and then what the computer does is uses tree search to evaluate future moves. Each choice of move is a branch on this tree, and it can look and say, for each move, what's the likely outcome? For each of those outcomes, what are the possible moves my opponent can make? For each of those outcomes, then what are my possible responses? And by fully going down this branching tree and looking at all the possibilities, the program can then figure out what its best choice is. Now, one of the things that makes Stockfish so clever and good at its game is it's very good at pruning this tree and ignoring moves that are unlikely to lead to any good end and not exploring them very far. But all told, this program is pretty useless at anything that is not chess. It is the opposite of general. So on our plot, we would put chess well above human level performance, but also very low on the generality axis. Now, compare that to Go, also a board game. If you're not familiar with it, there are 19 by 19 grid, and opponents take turns placing white and black stones. The rules are actually in some ways simpler than chess. At each turn, you pick a junction on which to place a stone. Now, the strategy, however, some argue is even more complex and, more importantly, more subtle. It's what is undoubtedly true is there are more possible board configurations. Where chess has an 8 by 8 board, Go has a 19 by 19 board. Where each piece in chess has a small prescribed number of motions, any stone in Go can be placed on any open junction. So when doing a tree search, the number of moves explodes much more quickly than in chess. Now, despite this, 2 years ago already, AlphaGo, a program built by researchers at DeepMind, beat Lee Sedol, a professional 9-dan player. Professional 9-dan would put him in the all-stars of the Go world. A later version, AlphaGo Master, was clocked with an ELO rating of 4858. Compare this to the highest rated human player, Park Jung-won, who's rated at 6669. So not only has Go beaten the best players of the world, but now already by a very healthy margin. Now, as we mentioned, the program understands the rules of Go, or knows the rules of Go, and uses the tree search to evaluate moves. Because there are so many possible board configurations, however, it can't memorize them all, so it uses convolutional neural networks to learn common configurations, and most importantly, it can see patterns that are not exactly repeated but are similar to things it has seen before. This is an important innovation, and we'll come back to convolutional neural networks in a few minutes. It also uses reinforcement learning on a library of human games to learn which moves are good. Reinforcement learning, in very straightforward terms, is looking at a configuration, an action, and the outcome, and learning the pattern. For a given configuration, if I take action A, good things happen. If I take action B, bad things tend to happen. After I learn those patterns, the next time I see configuration A, I can take the action that leads to good things. So using reinforcement learning on a library of human games then kind of bootstrapped AlphaGo and let it learn from the history of human play and human insights to get started. But like Stockfish, it's useless at anything that's not Go. So while it has a few tricks that allow it to be more general, it is still very narrow in its applications. So on our plot, we might put it here. Again, far exceeding human level performance, but still very low on the generality axis. Now let's take a jump to a different category entirely. Image classification. There is a wonderful data set called ImageNet, which has many thousands of images classified by hand by humans into 1,000 predefined categories. These categories include household items, cars and doors and chairs. It includes animals, giraffes, rhinoceroses. It also includes, for instance, many different species of dog. So it's not a trivial thing to take an image and accurately categorize it. And in fact, a typical human score on this is about 5% error. About 1 out of every 20 images, a human will classify incorrectly. So it's a tough task. In 2011, there began a large-scale visual recognition challenge in which teams got to put together their algorithms for classifying these images. And in 2011, the very best one got 26% error. So about 1 in every 4 image was wrongly classified. Still, 3 out of every 4 was correct, which was pretty amazing performance. Each year, this error rate decreased by close to half, which is an amazing rate of progress. Finally, in 2015, the error rate got lower than human. So we had a computer program classifying images better than a human does. Now, in 2017, one of the more recent competitions, more than half of the teams got fewer than 5% wrong. So now machines are routinely beating humans at this task. Pretty impressive. In terms of generality, this task is definitely harder, more general, more challenging than a board game. There are more variations, more possibilities. And to get at it, it uses convolutional neural networks, which are a deep neural network architecture specifically designed for finding patterns in two-dimensional arrays of data, like pixels or squares on a chessboard or on a Go board. They're very good at finding patterns that could be visually represented. This is good, but it has been shown to break easily outside of the set of images that you train it on. To give an example of this, if you look at the images on the right in the left-hand column, we see soap dispensers, praying mantis, a puppy. These are all images that were correctly categorized by a convolutional neural network. With the addition of a little bit of distortion, shown in the middle column, which you're seeing that correctly, it's just a little bit of noise, but the gray is no change at all, you get the images on the right. Visually to us, they look identical or very similar. You might be able to see a little bit of warping and distortion there. But for whatever reason, convolutional neural networks confidently predicted all of these to be ostriches. So this is not to say that they are not powerful and good, but they see something different than we are seeing. They are not learning to see in the same way that we see. Since then, the fragile nature of convolutional neural networks has been demonstrated through other ways. In some images, changing a single pixel, the right pixel to the right value, can change how that image is classified. Others have found that you don't even have to go into the digital domain. You can take carefully designed stickers and affix them to something and have that object be confidently classified as a banana, whatever it is. And in my favorite demonstration, a physical plastic turtle was rotated, and from every direction, the convolutional neural network confidently predicted that it was a turtle. Then, after just repainting a different pattern, not symbolic or representative of anything, but carefully chosen, that same convolutional neural network categorized it as a handgun. These examples show that, at least as currently done, our image classification generality is not quite where we would like it to be. So, definitely higher than human performance, but classifying ImageNet is a much narrower task than it might appear on the surface. So we'll put it pretty low on the generality axis. Now, here's a really fun example, video game performance. So again, the folks at DeepMind put together deep Q learning or deep reinforcement learning architecture to play video games. We'll talk about more about what that is in a second, but what they did is they took 49 classic Atari games and let the algorithm just look at the pixels and make random moves. And the algorithm didn't know if this was supposed to be a move left or a move right or a jump or a shoot. It just took moves and then used reinforcement learning to learn from the outcome and then learn this pattern of, oh, when I see this and I do this, either something good happens or something bad happens or something neutral happens. After doing that for long enough, it learned the patterns that let it choose the right thing to do. And in 29 of these 49 games, it did at or above human expert level play. And that was super impressive. So this is not just looking at a picture and saying this is a cat. This is looking at a picture in the moment and saying, for this particular instance, the right thing to do is jump. And then by jumping, that changes the image, and then having to respond to the new configuration and doing that again and again and again, and doing this better than a human. Now, the other part of this is there were 20 games then at which it did more poorly than a human. So after using convolutional neural networks to learn the pixel patterns, for which this is perfectly suited because the pixels are big and coarse, there's no noise, they don't change, the patterns are clear, so what the algorithm is seeing is very close to what we as humans see. And after using reinforcement learning to learn what actions to take in each situation, 20 of these games it wasn't able to match human performance on. And the pattern among those games is they tended to require longer term planning. One of them was Ms. Pac-Man. And if you ever played that, you know you're trying to eat all the dots in a maze while avoiding ghosts who are chasing you. It involves planning routes out several turns ahead, anticipating where ghosts are going to be. A lot of things that you can't get from a single snapshot and without thinking ahead several steps. In its current state, this algorithm didn't do that. And in fact, the game that it did the poorest on, a game called Montezuma's Revenge, required much more extensive planning, going to one location and grabbing an object so you could go to another location and open a door, and the computer just was not able to make those connections. So we'll add video games to our plot here. Again, more general than image classification. There's more going on. The task is broader, and performance is about human level. Now you may notice a pattern here. These fit roughly into a line or a curve, and we'll see this pattern continue. Looking at machine translation, taking text and changing it from one language to another. If you've ever gone to an online translator and typed in a phrase or copied a phrase from a language you weren't familiar with to one that you were, you will probably notice that the translation is surprisingly good at getting some of the sense, which is, even 5 years ago, was complete science fiction to be able to do this in a reliable way. You'll probably also notice that the result is nothing that a native language speaker would ever be likely to say. So it's okay, it's definitely in the right direction, but it's far from perfect. Now, what's really impressive to me about this is that the state of the art in language translation takes over 100 languages, and instead of having specific models to translate from each language to each language, all of these languages are translated to some uber intermediate representation, which is then able to be translated back into any one of these 100 plus languages. So an all-to-all language translator. So the sheer scope of that is really impressive. Now, in order to do this, it uses long short-term memory, LSTM, which is a neural network architecture, and it actually uses several deep neural networks in concert, one to carefully ignore parts of the input, one to choose what to remember, one to choose what to forget, one to choose what to pass on. There's quite a bit of computation involved. And this architecture uses several levels of those even. So the amount of effort and computing power thrown at this in general is, if we use one of our metrics as efficiency, it's could be considered a little bit of a hit, in addition to the inaccuracies. It is worth noting that this uses an attention mechanism. So I called out attention earlier as a possible limitation of human performance, but it also proves to be a really useful tool when dealing with a massive amount of information, too much to look at in depth. And so by pre-filtering and focusing down on what's most likely to be helpful, then an algorithm can be much more efficient in how it handles it. So for machine translations, amazing performance, still short of human, and for the wildly ambitious scope, it gets a little step up on the generality axis, a little bit of a hit on the performance axis. Translation is still a very small part of all the things that humans do, but I would definitely say this is more general than playing video games. Now, looking at recommenders. So if you think back to your last experience with an online retailer, probably the recommendations that you got were maybe 1 in 10 was really, really relevant. Some of the others were close but near misses, and some of the others were obviously way out in left field. So this is still pretty good. Like, this is a tough task. If you can imagine, like, back when there were video stores, going to a video store with your friend and trying to guess what your friend, even a friend you knew very well, would want to watch on a given night, you would be hard pressed to do better than like 1 in 3 or 1 in 4. So, 1 in 10 is not terrible, just ballpark. It's common to assume among these algorithms that order doesn't matter. So it just looks at everything you've ever bought today, yesterday, last year, and it doesn't think about how these things are related or how many you might have or how many you might need or how something that you bought previously might be related to what you might need tomorrow. It just looks at what people have bought in the past, what they've bought together. It also doesn't adapt to the fact that your selections might change with time. So even if you bought one jar of mayonnaise a year ago and then another one 6 months ago and another one a few months ago, it might not track the fact that your preference has changed. One of my favorite examples of these came up from Jack Rayner, Twitter user, who said, "Dear Amazon, I bought a toilet seat because I needed one. Necessity, not desire. I do not collect them. I am not a toilet seat addict. No matter how temptingly you email me, I'm not going to think, oh, go on then, just one more toilet seat. I'll treat myself." So recommenders, they do okay relative to humans. And I would argue that the knowledge of the world required to do really well is pretty deep. So we'll boost it up on the generality scale, but it takes a hit on performance. Now, we get to robots. Finally, something physical bumping around in the world, self-driving cars. Their performance is impressive. Taken overall per mile driven, self-driving cars' accident rates are lower than humans. And this is pretty amazing when you consider all of the things that a car has to deal with. Construction, pedestrians, bicycle riders, changing weather conditions, changing road conditions. They're not perfect, but they're surprisingly good. Now, in terms of generality, there are a few things that make self-driving cars less general than they might at first appear. And in fact, the biggest tricks to making them successful is to reducing the difficulty of the task, and so reducing the necessary generality of the solution. So one of the things that happens is, especially during training, humans still have to take over in some challenging situations. When the human gets uneasy or the car signals it doesn't know what to do, then it falls back to the human. And while driving is still a pretty complicated task, it's still very simple compared to, say, walking on rough terrain while eating a bagel and walking a dog who's pulling on the leash. There's a lot more to consider there, and it's a lot tougher than a car who is statically stable on 4 wheels on a road that's flat and mostly straight and mostly marked, and where the rules are well prescribed. To further simplify the task and narrow the scope of what needs to be learned, self-driving cars' driving style tends to be cautious. They definitely do not tend to speed. They tend to not follow closely or turn aggressively or do anything else that many human drivers do. This is absolutely good practice and should be lauded and is a model for all of us to follow. But what that means is that the raw driving skill required by a self-driving car is in general less than that required by a human. And it should also be noted that solutions are custom engineered for driving. The selection of sensors, the algorithms used to process them, the way everything's put together is not updated on the fly. It's gathered, evaluated by humans, and then very carefully and deliberately the heuristics, the rules behind how that's interpreted and processed are then updated and tested and released again. This makes sense for deploying anything that has such a high consequence as a car. But from a machine learning side, it means that the solution is actually not as general as it seems. It's very specific to a given car with a given set of sensors, and sometimes even to a given environment. Some self-driving cars, at least early failures, had to do with being deployed in climates that they weren't familiar with, for instance. So until their set of training data encompasses all of the conditions in which they will be deployed, they will be even narrower than human drivers. So all these things considered, on the task of driving in general, I chose to rate self-driving cars at lower performance than human. Still, it's physical interaction and it's interaction with other people and other cars. So it's quite a lot going on and definitely more complex than machine translation or even recommendations. Now, humanoid robots, the apex of cool applications. If you have not yet done it, get on the internet and search for robots doing backflips and check it out. When you see something like this, it is easy to make the jump to believe that robotics has been solved. Like when a robot can do physical feats of acrobatics that I can't do, then it's done. I'm ready to call it. And it's just, it puts a smile on my face that I can't wipe off. Now, in terms of generality, do another search for robots falling down, and you'll be treated to a montage of really humorous shorts of robots trying to do very simple things like open a door or lift an empty box or even stay standing up. And they really struggle with this. Because the systems are so complex, because the hardware and the sensors have so much going on, and because most of these are deployed as research projects, most of these activities are fairly hard-coded and pretty fragile. They make a lot of assumptions about the nature of the hardware, what's going on, the nature of the environment, and if any of these assumptions are violated, the robot's performance fails. So as a result, plotting them here, the generality in the sense that the types of things that they have experienced taken together as a whole are now getting to be a non-negligible fraction of things that humans can do. Maybe it's 0.1, maybe it's 0.01, somewhere in between, but an amazing set of things that can be quite hard. But performance is still sometimes laughably low compared to human level. We can, compare humanoid robots as agents to humans and see that it's much less. More interestingly here, our trend now is quite clear. there's a fat line here that runs roughly parallel offset from the human level intelligence line. As solutions tend to get higher performance, they also tend to get less general, and vice versa. But it's rare that we get big steps toward the human intelligence line. Now, this is what I think is cool. This is the whole point of this talk. There is one example that I would like to show of this before I jump to the conclusion, which is, again, from DeepMind, a program called AlphaZero. So AlphaZero is like AlphaGo, except everything it knows about Go has been taken out. It doesn't know the rules of any game now. It just sees visual patterns, tries actions, and learns to see what is successful and what's not. The way it was used is you can think of a brand new AlphaZero instance as being an infant in terms of the gameplay, and 2 AlphaZero infants were created, and they started to play each other. One was allowed to learn, the other one was not. So the one that learned gradually got just a little bit better, stumbling into some good moves by accident, until it became an okay beginner player of the game. Then it cloned itself. One of the 2 learned, the other did not, and they played and played until the one became an intermediate level player of the game. And it repeated this process of cloning and playing itself with one learning and the other not, and used its intermediate steps as scaffolding to get better and better. And it turns out that when using this approach with Go, within 4 hours, it was as good as the best human player. And within 8 hours, it had beat the previous best computer, its uncle, AlphaGo. Because it did not build any rules of the game, it was also able to learn chess and beat the current best chess playing program, Stockfish, and another board game called Shogi, and beat the current best shogi playing program as well, all of which beats humans by a wide margin. So this is cool because it does both better performance and it's more general. It's not specific to any board game. And presumably if there were other board games that had 2-dimensional grids and a set of rules that was not wildly different, it could learn to play those as well. So generality and performance. So what we have now is a point that is both farther to the right, higher performance, and farther up, higher generality than the original that it was from. So this is a real increase in area under that rectangle, an increase in intelligence. This is the direction that we want to go. So it's worth taking a step and taking a moment and thinking about what is it that allowed us to step in this direction? Well, AlphaZero made many fewer assumptions about what was going on. And it also was able to practice as many times as it needed to through self-play. In general, assumptions are what prevent generality. They enable performance, so if I build in knowledge of the rules of chess, I'm able to take advantage of those much more quickly, but it also prevents me from doing anything that's not chess. So if I turn that around, making fewer assumptions might mean it takes me longer to do something, but it means I might be able to learn to do more things. So some common assumptions. Sensor information is noise-free. We have ideal sensors. That makes sense if we're playing chess. When we sense that a piece is on a given square, we expect that it will be. But if we're dealing with, say, a self-driving car, maybe there's a smudge of mud on the camera, maybe the calibration of the LiDAR is off a little bit. We can't assume ideal sensors when we're interacting with the physical world. There are too many things we can't control for. Another common assumption is determinism. That's when I take an action, I know that it will have the same outcome every time. Again, makes great sense when I have a board game, Makes sense if I'm classifying images. If I say an image is an image of a cat, I know that it will be labeled as a cat image, right or wrong. However, if I'm a humanoid robot and I make an action to reach for a doorknob, the motor might not perform the way I expect. My feet might slip on the ground. I might have unanticipated challenges to my balance. The action may not turn out exactly as I expect, and I need to be able to adapt to this. Another really common assumption, unimodality. All of the sensors are the same type. So this is an assumption in convolutional neural networks, for instance. It's great at bringing in a two-dimensional array of information that is all the same type. It's all pixels, or it's all board squares. A general solution needs not to make this assumption. Another assumption, stationarity. This is a very common one. It's that the world doesn't change. The things that I learned yesterday are still true today. The things that I learned 5 minutes ago are still true right now. Now we have to make some assumptions about continuity. Otherwise, what I learned yesterday doesn't do me any good at all. But we also need to allow for the fact that the world has changed a little bit. Maybe the lubrication in my ankle joint is a little low, so it's going to respond differently than it did yesterday. Maybe there are clouds covering the sun, so the lighting conditions I learned to operate in yesterday have changed as well, and I'll need to be able to adapt to that. Another common assumption is independence, which is the world is not changed by what I do to it. Physical interaction violates this entirely. If I am a robot operating in a household and I bump into a chair and I scoot it 6 inches sideways, then whatever map I've made of that house will need to be changed a little bit. I have changed it myself. If I pick up a mug and move it from this table to that table, I have changed the position of that mug. The things that I do change the world, and I need to keep track of that. And any algorithm I use needs to be able to account for that. Another common assumption, ergodicity. Everything I need to know about how I operate, I can sense right at this moment. This is a common assumption, also known as a Markov assumption, but it's also commonly broken in physical interaction. For instance, if I can sense position, that's great, but that doesn't tell me anything about velocity. And sometimes I need to know velocity to know how to respond to something. Another assumption that is very common is that the effects of my actions become apparent very soon. This is something that does not hold true, for instance, in chess, where the opening move will affect whether or not I win many, many time steps away. There are different tricks for handling this in chess, for instance, assigning point values to intermediate positions of pieces on the board. But in physical interaction, it's much more difficult to do this, to know that given a set of actions that I take right now, which is most likely to result in something that's desirable 5 minutes from now or a day from now. All of these assumptions are very common in the algorithms currently being used that we call AI. These algorithms are not sufficient for achieving human-level intelligence. These assumptions will prevent them from doing that. So one thing that all of these assumptions have in common is that they do not hold when you're working with humanoid robotics, or in fact, any robot that's physically interacting with the world. So my proposal is that focusing on physical interaction is a great way to force us to confront these assumptions, to find out which ones we can bend, to find out which we can avoid altogether, and to drive us to create algorithms that are less fragile and able to accommodate a much more general set of tasks. That will then take us one step closer to human-level intelligence. When you hear about artificial intelligence, about a half of the time, what people are talking about is convolutional neural networks. Understanding how they work is really helpful in getting a peek behind the curtain at the magic of artificial intelligence. So we're going to walk through it in some detail. Convolutional neural networks takes images, and from them, they learn the patterns, the building blocks that make them up. So for instance, in the first level of this network, you might learn things like line segments that are at different angles. And then at subsequent layers, those get built into things like faces or element of cars, depending on the images that you train the network on. You can pair this with reinforcement learning algorithms to get algorithms that play video games, learn to play Go, or even control robots. So to dig into how these work, we'll start with a very simple example, much simpler than all of these. A convolutional neural network that can look at a very small image and determine whether it's a picture of an X or an O. Just two categories. So for example, this image on the left is an 8 by 8 pixel image of an X. We want our network to classify it as an X. Similarly, with the image of the O, we want the network to classify it as an O. Now, this is not entirely straightforward because we also wanted to handle cases where these inputs are of different sizes, or they're rotated, or they're heavier, or they're lighter, and every time we'd like it to give us the correct answer. A human has no problem looking at these and deciding what to do, but for a computer, this is much harder. When trying to decide if these two things are equal, what it does is it goes through pixel by pixel. Black pixels might be a -1, white pixels might be a +1, and it'll compare them pixel by pixel, find the ones that match, and here the red pixels are the ones that just don't match. So a computer looking at this would say, no, these are not the same. They have some matches, but they have a lot that don't match. So the way convolutional neural networks do this, one of the tricks they use is that they match pieces of the image. So you can look at these pieces and shift them around a little bit, but as long as the tiny bits still match, then the overall image is still considered a pretty good match. So these tiny bits might look like this. We'll call them features. You can see the one on the left looks like a diagonal arm of the X that's leaning left. The one in the middle looks like the center of the X where it crosses. And the one on the right looks like a diagonal arm leaning right. And you can see how these different pieces, these different features of the image, match different patches within the overall image. So the math behind finding this match, applying features, is called filtering. It's pretty straightforward, but it's worth walking through. The way that it's done is you line the feature up on the image patch you're concerned with, multiply pixel by pixel, add up the values, and then divide by the total number of pixels. This is one way to do it. Here, for instance, we start with this feature of the arm of the X leaning left. We align it with this arm on the image, and we start with the upper left pixel, and we multiply both values. 1 by 1 equals 1. Now, because we started with the upper left pixel, we can keep track of our answers here. So this pixel, when multiplied, equals 1. The upper center pixel is -1 in both the feature and the image. So -1 times -1 is also equal to 1. So that when you multiply them and you get a 1, that indicates a perfect and a strong match. And we can continue doing this throughout the entire feature and the entire image patch. And because they are a perfect match, every single one of these matches will come back as a 1. And so to find the overall match, we just add up all these 9 ones, divide by the total number, which is 9, and we get a match of 1. Now we can create another array to keep track of how well the feature, when placed in this position, matched our image. So this average value is 1. We'll put a 1 right there to keep track of that. You can see what it looks like if we were to move this feature then and align it to a different patch. So let's say we move it down to the center of the X and we go pixel by pixel and find what matches. And after a few pixels, we actually find one that doesn't match. We end up with a -1 times a +1, giving us a -1 back. This indicates a non-match of these pixels. And as we go through the rest of the feature, we can see that there are a couple of pixels that don't match. So here, when we add these up and divide by 9, we get a number that's less than 1, 0.55. So it indicates a partial match, but not a perfect one. It turns out you can go through and do this for every possible location in the image. You can chop it up into every possible image patch, compare the feature to each one, and here's what you would get in this particular case. This is what convolution is. It's taking a feature and applying it across every possible patch across a whole image. And you can see here why it's called filtering. What we have is a map of where this feature matches the image. You can see a strong bunch of +1s on the diagonal line from the lower right to the upper left, and then lesser values everywhere else. So it's a filtered version of the original image that shows where the feature matches. You can do this, we can represent this with this notation. We just invented this little convolution operator for shorthand. And we can do this with our other features as well. We can see where our center X matches. Not surprisingly, it matches strongest in the center of the image. We can see where our leaning right arm matches. And not surprisingly, it matches along this diagonal from the lower left to the upper right. We have 3 filtered versions of the original image. So this is what a convolution layer in a convolutional neural network does. It has a set of features in it, and it can be 3 or 30 or 300 or 3,000, but it has a set of features, and it takes the original image and returns a set of filtered images, one for each of the features. So this is how we'll represent it. That's the #1 ingredient in convolutional neural networks. That is the magic special sauce, the special trick that gets from a non-exact match and lets the algorithm is able to pull out, okay, well, it's not a perfect match, but it's still a pretty good match because it does this convolution and moves the feature across the image and finds everywhere that it might match. Another piece of this is called pooling. So we took our original image and now we have a stack of images. What this step does is it shrinks it down a little bit. We start by picking a window size, usually 2 or 3 pixels, picking a stride, usually 2 pixels, has been shown to work well, and then walking this window across the filtered images, and then from each window, taking the maximum value that you see. So this is called max pooling. So to see how this works, we start with one of our filtered images. We have our window, which is 2 pixels by 2 pixels. And within that, the maximum value is 1. So we create another little array to keep track of all of our results, and we put a 1 in it. And then we step it over by our stride, which is 2 pixels. Look at the window, choose the maximum value. In this case, it's 0.33. Record it, and go again. And we keep doing this, recording the maximum value each time, all the way through the image. And when we're done, we have, which if you squint, looks like a shrunken version of the original. We still have this strong set of +1s on the diagonal from upper left to lower right, and then everywhere else it's less than that. So it maintains kind of the original signal, but shrinks it down, kind of picks off the high points And this gives us a smaller image, but still similar to the original. And we can just represent it with this little shrinking arrow. We can do this with each of our filtered images. And again, you see that very roughly the pattern of the original is maintained. So in a pooling layer, a stack of images becomes a stack of smaller images. Now, the last ingredient we need is normalization. So this keeps the math from breaking. By taking and tweaking these values just a little bit, it takes everything that's negative and changes it to 0. This keeps things from becoming unmanageably large as you progress through subsequent layers. This function is called a rectified linear unit. It's a fancy name for something that just takes anything that is negative and makes it 0. So a 0.77, not negative, it doesn't touch it, but a minus 0.11, it's negative, just bumps it up to 0. And by the time you've gone through all of your images and done this, all of your pixels and done this, this is what you have. So everything that was negative is now 0. So just a nice little bit of normalization, some conditioning to keep things numerically well behaved. So a stack of images becomes a stack of images with no negative values. Now, you can notice that the output of one layer looks like the input to the next. They're always arrays of numbers. An image and an array of number are the same thing. They're interchangeable. So you can take the output of the convolution layer, feed it through the rectified linear unit layer, feed that through the pooling layer, and when you're done, you have something that has had all of these operations done to it. And in fact, you can do this again and again. This recipe, you can imagine making like a Scooby-Doo sandwich of all of these different layers again and again and in different orders. Some of the most successful convolutional neural networks are kind of like accidentally discovered groups of these that just happen to work really well, so they get used again and again. So over time, each convolution layer filters through a number of features. Each rectified linear unit layer changes everything to be non-negative, and each pooling layer shrinks it. So by the time you're done, you get a very tall stack of filtered images with no negative values that has been shrunken down in size. Now, by the time we've gone through several iterations of this, we take and run it through a fully connected layer. This is more of a standard neural network where every input gets connected to everything in the next layer with a weight. Every single value, you can think of it as a voting process. So every single pixel value that's left in these filtered shrunken images gets a vote on what the answer should be. And this vote depends on how strongly it tends to predict an X or an O. When this pixel is high, is this output usually an X or is it usually an O? So you can see for this particular input, the input was an X. Here's what the imaginary convolved and filtered values are. And over time, we would learn that these things that are high when it sees an X get a strong vote for the X category. Similarly, if you have an input that's an O, these final pixel values that tend to be really high when the right answer is O, gives a strong vote for the O category. The thicknesses of these lines represent the weights, the strength of the vote between these pixels and these answers. So now if we get a new input that we've never seen before, these might be the final pixel values, we can use these votes and do a weighted voting process for both of these, add them up, and in this case, it's a 0.92 total for X and a 0.51 total for O. 0.92 is obviously more than 0.51. We declare X the winner. So this input will have been categorized as an X. So this is a fully connected layer. So it just takes a list of feature values, in this case our filtered shrunken pixels, and it becomes a list of votes for each of our output categories, in this case an X or an O. Now these can also be stacked. You can have like little, they call them hidden layers, but like secret hidden categories in between here. So one votes on the first layer, votes on the first set of hidden categories, and then those vote on the next layer and so forth until you get to your final ones. We'll dig into this more in just a little sec, but these all stack onto the end. Now to go into the next level of detail on these neural networks, set aside our X and O detector for a while. There we had 8 by 8 pixel images, so 64 pixels in all. Consider now a 2 by 2 pixel image, so just a 4 pixel camera. And what we would like to do is categorize the images that it takes as either being a solid image, all light or all dark, a vertical image, a diagonal image, or a horizontal image. Now the trick here is that simple rules can't do it. So both of these are horizontal images, but the pixel values are completely opposite in both of them. So you can't say, well, if the upper left pixel is white and the upper right pixel is white, then it must be horizontal, because that's violated by the other one. Now, of course, you could do more complicated rules to do this. The point is that when you go to larger images, you can't make simple rules that capture all the cases that you want. So how do we go about it? We can take these 4 input pixels and break them out. We call them input neurons, but they just take these pixels and turn them into a list of numbers. The numbers correspond to the brightness. -1 is black, +1 is white, 0 is middle gray, and everything else is in between. So this takes this little image and turns it into a list of numbers. That's our input vector. Now each of these, you can think of it as having a receptive field. This is an image which makes the value of this input as high as possible. So if you look at our very top input neuron, the image that makes that number as high as possible is an upper left pixel that's white. That makes the value of that 1, and it doesn't care what the other pixels are. That's why they're checkered. So you can see that each of these has its own corresponding receptive field, the image that makes the value as high as it can go. Now we're going to build a neuron. So when people talk about artificial neural networks and a neuron, we are going to build it bit by bit. The first thing you do to build a neuron is you take all of these inputs and you add them up. So in this case, this is what we'd get. So the neuron value at this point is 0.5. Now the next thing we do is we add a weight. We mentioned the weighted voting process before. So what that looks like is each of these inputs gets assigned a weight between plus and minus 1, and the value gets multiplied by that weight before it gets added. So now we have a weighted sum of these input neurons. And we will represent this visually by showing positive weights in white, negative weights in black, and the thickness of the line being approximately proportional to the weight. And when the weight is 0, we'll leave it out to minimize visual clutter. So now we have a weighted sum of the inputs. The next thing that we need to do is squash the result. So because we're going to do this a lot of times, it's nice if we always guarantee the answer is between plus and minus 1 after each step. That keeps it from growing numerically large. A very convenient function is this S-shaped, so sigmoid squashing function. This particular one is called the hyperbolic tangent. There is confusingly something else that's called the sigmoid. It's a little bit different, but the same general shape. But the characteristic of this is that you can put in your input, draw a vertical line, see where it crosses the curve, track that over to the using a horizontal line to the y-axis, and you can see what the smashed version, the squashed version of your number is. So in this case, 0.5 comes out to be just under 0.5. 0.65 comes out to be about 0.6. And as you go up this curve, you can see that no matter how large your number gets, what you get out will never be greater than 1. And similarly, it'll never be less than minus 1. So it takes this infinitely long number line and squashes it so that it all falls between plus and minus 1. So we apply this function to the output of our weighted sum, and then we get our final answer. So this weighted sum and squash is almost always what people are talking about when they talk about an artificial neuron. Now we don't have to do this just once. We can do it as many times as we want with different weights. And this collection of weighted sum and squash neurons is, you can think of it as a layer, loosely inspired by the biological layers of neurons in the human cortex. So each of these has a different set of weights. Here, to keep our picture really simple, we'll assume these weights are either +1, white lines, -1, black lines, or 0, missing entirely. So in this case now, we have our layer of neurons. We can see that the receptive fields have gotten more complex. If you look at the neuron in the first layer on the top, you can see how it combines the inputs from the upper left pixel and the lower left pixel. Both of the weights are positive, those lines are white, and so what comes out, its receptive field is, if both of those pixels on the left are white, then it has the highest value it can possibly have. If we look at that layer of neurons and look at the one on the bottom, we can see that it takes its inputs from both of the pixels on the on the right. But it has a negative weight connecting it to the lower right neuron. So its receptive field, what maximally activates it, is a white pixel in the upper right and a black pixel in the lower right. Now, we can repeat this because the outputs of that first layer of neurons looks a whole lot like our input layer. Still a list of numbers between -1 and 1. And so we can add additional layers, and we can do this as many times as we want. Each time, each neuron in one layer is connected to each neuron in the other layer by some weight. So in this case, you can see how the receptive fields might get still more complex. And now we're starting to see patterns that look like the things that we're interested in: solids, verticals, diagonals, horizontals, by combining these elements. Now there's one more thing that we can do. Remember our rectified linear unit. We can have different neurons here. And instead of a weighted sum and squash, we can just have something that takes the input and spits out 0 if it's negative, and the original value if it's positive. And so for instance, if we have an input whose receptive field is the one on the very top in the second layer, all solid white, and we connect it with a positive weight to the rectified linear unit neuron on top, then of course what would maximize that is an all solid white input. But if we look at the neuron just below that, that's connected to it with a negative weight, then that flips everything around, and what maximally activates that is an input that's all solid black. Now we're really starting to get the set of patterns that we can imagine using to decide what our image is. So we connect these again to a final output layer. This output layer is the list of all the possible answers that we expect to get out of our classifier. Originally, it was X's and O's. Now it's 4 categories: solid, vertical, diagonal, and horizontal. And each of these inputs into them have a vote, but you can see that very few of them are connected. This network assumes that most of those votes are 0. So to see how this plays out, let's say we start with an input that looks like the one on the left. This is obviously a horizontal image with a dark bar on top and a white bar on the bottom. We propagate that to the input layer, and then we propagate that to the first hidden layer. And you can see, for instance, the neuron on the very top, it combines 2 input neurons that one is light and one is dark. So you can imagine it summing a +1 and a -1 and getting a sum of 0. So that's why it's gray. its value is 0. Now, if you look at the neuron in the very bottom, in that first hidden layer, you can see that it sums also an input that is negative and one that's positive, but it's connected to one by a negative weight and the other by a positive weight. So it actually, what it sees, its weighted sum is -1 and -1. So what it is getting, you can see, is the opposite of its receptive field. So that means it's maximally activated, but negatively. So that's why it's black. We move to the next layer, and you can trace these things through. So anything 0 plus 0 is going to get you 0. If you look at the neuron on the very bottom of this second hidden layer, you can see that, yes, it's adding up a negative and a negative, both connected by positive weights, so it's also going to be negative, which makes sense because you can see that its receptive field is the exact opposite of what the input is right now. So it's maximally activated, just negative. And then when we track this to our next layer, you can see that following that bottom pair of neurons, because it's a negative value, it goes through the rectified linear unit and becomes 0. So that's gray. But if you look at the very bottom neuron there, it's connected with a negative weight. So it becomes positive. So that rectified linear unit really likes it. So it gives it a maximum value. So everything is 0 except for that neuron on the bottom. And then finally, what that means is that the only output that is non-zero is this horizontal one. So this network would classify the input image as being horizontal because of this. Now, there's some magic here. Where did we get those weights? Where did we get the filters in between? This is where we start to get down to when we talk about learning, adaptation, the learning in machine learning, it is all about optimization. These are learned through a bunch of examples over time. So we're going to set that aside for just a minute. We'll come back to how those get learned, but we need to talk about optimization first. So consider drinking tea. There is a temperature range where it is a delightful experience. It's warm and delicious and comfortable. If your tea is too much hotter than that, it's very painful and not good, not fun at all. And if your tea is cooler than that, it's lukewarm and it's really meh. It's really not worth your time. So this area at the top is the peak. This is the best. This is what we're trying to find in optimization. We're just trying to find the best experience, the best performance. Now, if we want to find that mathematically, the first thing we do is we flip it upside down, just because this is how optimization problems are formulated. But it's the same type of thing. Instead of maximizing tea drinking pleasure, we want to minimize tea drinking suffering. We want to find the bottom of that valley, the lowest possible suffering. There's a few different ways we could do this. The first is to look at every point on this curve and just pick the lowest one. Now the trick with that is we don't actually know what this curve is beforehand. So in order to pick the lowest one, we have to do exhaustive search, which in this case would be make a cup of tea, have someone drink it, ask them how they like it. Make another one, ask them how they like that one. Do it again and again for every possible temperature, and then pick the one with the lowest suffering, the most enjoyment. This is effective, very effective. Also, it can be very time consuming for a lot of problems, and so we search for a shortcut. Now, because this is a valley, we can use our physical intuition and say, hey, well, what if we just had a marble and we let it roll to the bottom of this valley? We wouldn't have to explore every single piece of it. So this is what's behind gradient descent. The way it works is we start not knowing anything about this function. We make a cup of tea, someone tells us how they like it, and then we change the temperature a little bit. We make another cup of tea, just a little bit cooler. And we ask someone how they like that, and we find out they actually like it just a little bit less. That tells us what direction we need to go. We need to make our next cup of tea warmer. And the change, the difference between how much they liked those two, tells us the slope, it tells us the steepness, it gives us a sense of how much warmer we can expect to make that next cup of tea. So we make another one, and we repeat the process, and then we, again, scoot a little ways off to the side, make another cup of tea, and figure out, again, which direction we need to go. Do we need to go warmer to make a better cup or cooler to make a better cup? And we repeat this until we get to the bottom of the curve. You'll know you're at the bottom when you change the temperature just a little bit, and the tea drinker says, yeah, it's exactly the same. I like that just as much as the last one. That means that you're there kind of at the flat bottom of the valley. So gradient descent is the first level trick for brewing fewer cups of tea. There's another thing you can do, which is to use curvature. This is kind of an advanced method, is you can make your original cup of tea and then make one a little bit warmer and one a little bit cooler, and you can look to see how that curve of your function goes. And if it's very steep and getting steeper, then you know you can take a giant step because you're probably not anywhere close to the bottom. And then you can do it again, and if that curvature is starting to bottom out, then you can take a smaller step because the signal that you're getting closer to the bottom, and it helps you to do this in fewer steps as long as your curve is relatively well behaved, which is not always the case. So ways that this can break, imagine we're doing this on a hot day, and actually it turns out that if we were to cool our tea way down, we'd get a really nice iced tea, which turns out to be even more popular with our tea drinkers. But gradient descent would never find this. Gradient descent always rolls down to the bottom of the nearest valley. It doesn't hop around to see if there are any valleys hiding anywhere else. Another problem is, let's say there's a wiggle on our curve. There's something happening in the environment. We have noisy buses driving by, and it affects how people enjoy their tea. We might not be able to find this very lowest dip because we might get stuck in a dip further up the curve. Similarly, if we ask our tea drinkers to rate their tea drinking experience on a scale from 1 to 10, we get these discrete jumps in our function. And if you imagine a marble rolling downhill, downstairs, it doesn't always work well, and it can get stuck on a step without making it all the way to the bottom. Now, all of these things happen in real machine learning problems. Another one, imagine you have really picky tea drinkers, and if the tea is anything but perfect, they hate it, hate it, hate it. And so you have these plateaus on either side, and there's no signal to tell you that if you move in a little bit, you'll find that deep valley. So for cases like this, of course, we can always fall back to exhaustive exploration. It will find the best answer in every single one of those cases. But a lot of times, we just don't have the time. Like, if I have to brew and measure the drinking pleasure of 10 million cups of tea to get a good answer to this, it's not going to happen in my lifetime. So luckily, there are some things in the middle that are more sample efficient than exhaustive exploration, but a little bit more robust than gradient descent. Things like genetic algorithms, simulated annealing, things that their defining characteristic is they have a little bit of random jumping around. They're a little bit of unpredictability. And so they make it harder to slip things by them. They all have their strengths and weaknesses. They tend to be good for different types of problems or different types of pathologies in your loss function, but all of them help avoid getting stuck in the local minima, the little small valleys that gradient descent will get stuck in. They get away with this by making fewer assumptions, and they can take a little longer to compute than gradient descent, but not nearly so long as exhaustive exploration. You can think of gradient descent as being like a Formula One race car, and if you have a really nice, well-behaved track, it is fast. But if you put a speed bump in the track, you're done. Genetic algorithms, simulated annealing, evolutionary algorithms, those are like, a four-wheel drive pickup truck. You can take a fairly rough road with those and get where you're going. You won't get there in record time, perhaps, but you'll get there. And then exhaustive exploration is like traveling on foot. There is nothing that will stop you from getting anywhere. You can travel literally anywhere, but it just might take you a really, really long time. So to illustrate how this works, imagine we have a model that we would like to optimize. We have a research question. How many M&Ms are in a bag of M&Ms? So answering this is easy. You buy a bag of M&Ms, you eat it, 53. You can count those M&Ms. So great, we know how many were in the first bag. Now when I did this, I made a mistake and I bought another bag and I tried that one and I got a different answer. So now I can answer 53 or I can answer 57. Either way, I'm only right half the time because I can't capture both bags with one answer. And I could answer somewhere in the middle, but that's never right. I have never opened a bag that had 55 M&Ms in it, so it's unclear that that's the right answer either. And the situation does not improve with the more bags of M&Ms that I ate. It just gets a little bit out of control. And so I changed my goal from answering the question right to answering the question in a way that is less wrong. So in order to do that, I have to get really specific about what I mean by how wrong I am. And to do that, I have this distance function, this deviation, which is the difference between my actual guess and the actual number of M&Ms in a bag. So we call for bag number I, this deviation is d sub I. It's just the difference between the guess and the actual number. And then I have to take this deviation and turn it into a cost. So one common way to do this is to square it. It's nice, as the further away things get, kind of the more costly it is perceived as, and it goes up faster. So if there's a bag that's off by twice as much as another, the cost is 4 times. So it penalizes the things that are way off. The things that are close, it doesn't penalize so much. And if we don't care, if we don't want to overly penalize the things that are way out there, we could use the absolute value of the deviation. So if it's off by twice as much, it'll just be twice the cost. But really, we could use anything. We could use the square root of the absolute value. We could use 10 to the power of the absolute value of this deviation. Anything that goes up, the further away you get from 0. We'll stick with squared deviation. This is super common. It has some nice properties and makes for a good example. So for the total cost of any guess that we make, if I guess n estimated bags, M&Ms in a bag, then the loss function, this fancy curly Q L, of that guess is just adding up the square of the deviation associated with each bag of M&Ms, d1 through dm squared. So each deviation is actually the number of M&Ms in that bag minus the guess. So I square that. And we can write that with fancy summation notation like this. So this is my loss function. This is the total cost. This is how wrong I am when I make a guess, n est. So because we have computers, you can write a little bit of code and you can do exhaustive exploration. And I can say, if I guess anything between 40 and 70, how wrong would I be with this data? And you can plot it, and visually we can look at this and we can say, hey, look, there's the lowest value. And we can say, what is the value of the guess that gives me the lowest loss? That's what that notation means right there. And this best guess is just about 55.5 M&Ms. Problem solved. So this is an example of numerical optimization, where we calculate this loss function, and then we can do, essentially, because it's simulated, we can do exhaustive exploration and just pick off the lowest value. Now, for this particular example, there's a fun other way to find it. We know at the bottom of this curve, the slope is 0. It's the only place in the whole curve where that's true, where it's flat. We can use a little bit of calculus to find that. Feel free to tune out if calculus is not your thing, but it's not too bad. So we find the slope of the loss function with respect to our guesses, and we set it equal to 0, and we solve it to find for what guess is that true. So we take our loss function, this sum of the square of the differences of the count and the guess, and we take the derivative of that with respect to our guess. And the derivative of a sum is the same as the sum of the derivatives. We take the derivative of that, just bring down the exponent, so 2 times that, summed. Because all that's equal to 0, we can divide it by 2 and it'll still be true. So now the sum of our deviations is 0. So to further simplify this, it's the sum of all of the counts of the actual bags times the sum of our guess once for each bag. If we have m bags, then it's m times our guess. And then we can move that to the other side of the equal sign and divide both sides by the number of bags, m. And what we get is that our best guess is the sum total of the number of M&Ms we found in all the bags divided by the number of bags, or the average count per bag. So this is a really slick result, and it's things like this that make people so excited about optimization. With a little bit of math and calculus, you can get this nice theoretical result. Now it's worth noting that this is only true if you use deviation squared as your cost function. So that's one reason people like it so much, is because it tends to give some nice results like this. But there is this analytical shortcut to find what the best guess is. We're going to come back to this in a few minutes. Now, how does optimization change? How do we use it in our neural network to find these weights and these features? So what we want to do, we know what our error function is. It's how wrong our guesses are. So in this case, we have a labeled data set, which means that a human has already looked at this input on the left and has said, hey, that's a horizontal image. The truth values are what we know should be the right answer. 0 votes for everything except horizontal. That should have a vote of 1. So let's say initially we've got a neural network that all the weights are random, and it gives us nonsense results. It says, well, yeah, everything has some number associated with it, but it's nothing like the right answer. Well, we can find the error for each category and add it up and find a total error, and this is how wrong our neural network would be for this one example. Here's our loss. Here's our error. Now, the idea with gradient descent is we're not just adjusting one thing. We're not just adjusting our guess of the number of M&Ms. We're adjusting many things. We want to go through and adjust every single weight in every single layer to bring this error down a little bit. Now, that is a little bit challenging to do, because in order to do that, one thing you can do is find a analytical solution like we did before, to go through and move our guess a little bit up and a little bit down and find the slope is really expensive when you consider that this is not a one-dimensional problem anymore. It might have hundreds or millions of different weights that we need to adjust. So calculating that gradient, that slope, requires hundreds or millions of more passes through the neural network to find out which direction is downhill. Enter backpropagation. So remember, we found the nice analytical solution to what we had going on in the case of the M&M estimate. So we would love to be able to do something like that again. If we had an analytical solution, we could jump right to the right answer. So slope, in this case, it's change in weight, it's change in error for a given change in weight. That's the slope here. So there's lots of ways to write that, but delta error, delta weight, d error, d weight, we'll use this partial error, partial weight, just because it's most correct. But all these things mean the same thing. If I change the weight by 1, how much will the error change? What is the slope? So in this case, it would be -2, and we would know that we need to increase the weight in order to get closer to the bottom. This tells us not only the direction we need to move, but gives us a sense of about how far we should go. Doesn't tell us exactly where the bottom is, but it tells us which way it needs to adjust. Now, if we do know the error function example, we can make an analytic solution, and we can calculate that slope exactly. So in this case, the change in error for a given change in weight is just the derivative of our error function here, which is, in this case, is the weight squared. So the derivative is 2 times the weight. The weight is -1, and so the answer is, a slope of -2. That tells us what we need to know about which way to adjust. Now with neural networks, of course, they're a lot more complex than that, but we can actually analytically compute the slope of the function where we are. We don't know where the minimum is, but we can find the slope without having to recalculate the value of everything each time. And this is how it works. Imagine the world's most trivial neural network that has 1 input, 1 output, 1 hidden layer with 1 neuron in it. So it's got an input connected by a weight, W1, to an intermediate value connected by a weight, W2, to an output value. So the intermediate value is just x times that weight. So the derivative of y with respect to the weight is x. What that means is if I change W1 and I move it by 1, then the value of y will change by the value x, whatever x is. We have the slope of this piece of the function. Similarly, it's straightforward. We can just read off that whatever the value of y is, multiply it by the weight W2, we get e. So if we want to find the slope of the error function for a given change in y, the answer is W2. If I changed y by 1 unit, then the error changes by the amount W2. Now, chaining means that we can take these two things and just multiply them together. So by inspection, we can see that in this little neural network, if we take x, multiply it by W1, multiply that by W2, we get the error e. Now what we'd like to know is if I change that W1 by a certain amount, how much does the error change? Well, in this case, we just take that whole expression and take the derivative with respect to W1. And fairly trivial bit of calculus, it comes out to be x times W2. And what we can see then is we can substitute in these steps, this change in y with respect to W1 is the same as x. W2 is the same as the change in error with respect to y. And what this breaks down is if we want to step down the chain, we want to know how much a change in W1 affects the error. What is dE dW1? We can actually break it down into steps and say, okay, well, if I change W1, how much does y change? And then if I change y, how much does the error change? This is chaining, and this is what lets us, if we know which way we want to change the error, it lets us calculate how much we can change this weight to help that happen. And there's nothing to prevent us from doing this again and again. If I have a weight that's deep into my neural network and I want to know how much my error is going to change if I tweak it up or down, I want to know the slope of my loss function with respect to that weight, then I can just break it down and say, okay, well, if I change the weight, how much does A change? If I change A, how much does B change? If I change B, how much does C change? And chain it all the way down. Now, it's called back propagation because in order to calculate it, we actually need the value at the end. We have to start with the error value in order to calculate each of these all the way back down into the depths of the network. But still, we can do that. Now, the reason you have to go backwards is that, let's say we want to know what this should be. If I change A, how much does the error change? It's like, well, let's assume that I already know how much the error is going to change. If I change B, what is this back propagation step? What is the additional link I need to add to this chain? It's like, well, it's how much does B change if I change A? If they're connected by a weight, then how do I incorporate that weight? We know that two neurons connected in this way are represented by this. B is the weight times the value of A. And so we can just take a little derivative here and get the change in B with respect to A is W. So this step in the backpropagation change can be represented by whatever that weight is. Cool. Now we know that we have sums in our neural network. That's another thing we have to handle. If I know how much my error changes with a change in Z, then how much would it change with a change in one of the inputs to Z, where that input goes into a sum? Well, I can write the expression for Z, adding up all the inputs. If I want to know how much Z changes with respect to a change in A, I just take the derivative, and it turns out to be 1. So this is a trivial backpropagation step. Now, the most interesting one of all, if I know how much the error changes with respect to a change in B, and then I want to know how much it changes with the input to that sigmoid function, then I can just say, okay, well, a sigmoid function mathematically looks like this, and I can take the derivative of B with respect to A. And one of the beautiful things about the sigmoid function is that the derivative actually looks like this. It's just the value of the function times 1 minus the value of the function, which is one of the reasons that sigmoids perhaps are so popular in deep neural networks. So this step is also straightforward to calculate. In none of these steps have we had to recalculate all of the values in the neural network. We've been able to rely on things that have already been calculated, what the values are at each of these neurons. That's what makes backpropagation so mathematically efficient, and is what allows us to efficiently train neural networks. That is why each element in a neural network, no matter how exotic it is, needs to remain differentiable so that we can go through this exercise of finding what the link in the chain is when we're doing the chain rule on our derivatives, so that we can compute the backpropagation. We can backpropagate it. And again, rectified linear units, if we know how much the output affects a change in error, we want to know how that extends to the input, we can write the function of a rectified linear unit, we can take the derivative of it, and then use that in our chain rule. So imagine now that we have this labeled example. We calculate the answer that this random neural network that's not special at all, it'll give an answer that's completely wrong, and then we backpropagate the error and adjust every one of those weights a little bit in the right direction. And we do that again and again. And after we do that a few thousand times, this stochastic gradient descent goes from this fully connected, totally random neural network to something that is a lot more efficient and that is able to give answers that are much closer to the right answer. So coming back up to our convolutional neural networks, these are the fully connected layers. That's how they're trained. They can also be stacked. This backpropagation applies not only to these fully connected layers, but also to the convolutional layers and the pooling layers. We won't go through and calculate the chain rule for them, but you can do that as well. And going through this whole stack of different layers gets trained on a bunch of examples, in this case, of labeled X's and O's. Give it a bunch of inputs that we know the right answer to, and we let it adjust all of those connections. Not only that, it also adjusts all of the pixels in the features for each convolutional layer. So it learns not only the weights, but also the features. And then over time, those representations become something that lets it predict very well what is an X and what is an O. On top of that, there are other things that we can use optimization for. So there's a bunch of decisions here that we haven't addressed yet. How do we know how many features to put in each convolutional layer? How do we know how big those should be? How many pixels on a side? How do we choose the size and stride of our pooling windows? In our fully connected layers, how many layers do we have and how many hidden neurons do we put in each? Each of these decisions are called hyperparameters. They are also values that we get to choose, but they're the next level up. They kind of control how everything happens below. And in order to see how well they perform, we have to train the whole thing on all the images start to finish. So, but the same principles apply. We can adjust these and choose them to get the best result possible. In a lot of cases, it's worth pointing out that there's just not enough computation available in the world to try out all the possible examples. And so what we have right now are some recipes, some things that researchers have stumbled onto that seem to work well and that get reused. But there are a lot of places, a lot of combinations of these hyperparameters that actually haven't been tried yet. And so there is always the possibility that there are some combinations that work even much better than what we've seen so far. Now, we don't have to use convolutional neural networks for just images. Any two-dimensional or three-dimensional data works well. The thing that matters is that in this data, things that are closer together are more closely related than things far away. It matters if two things are in adjacent rows or in adjacent columns. So in images, this is plainly the case. The location of a pixel in an array of pixels is part of the information. If you were to randomly jumble the rows and columns, that would lose the information that's there. That's what makes this well suited to convolutional neural networks. Anything that you can make look like an image may also be suited to convolutional neural networks. For instance, if you're working with audio, you have a really nice x-axis. Your columns can be subsequent time steps. You don't want to jumble those because the time, the order in which things occur in time matters. And you can make your rows the intensity in different frequency bands, going from low frequency to high frequency. Again, the order matters there. And so being able to take sound then and make it look like an image, you can apply this processing to it and find patterns in the sound that you wouldn't be able to find conveniently any other way. You can also do this with text with a little bit of work. You can make each of your rows a different word in the dictionary, and then you can make your columns the position in sentence or a position location that it occurs in time. Now, there are some limitations here. Convolutional neural networks only capture local spatial patterns. So if your data can't be made to look like an image, or if it doesn't make sense to, then they're less useful. So for example, imagine you have customer data that has columns representing things like names and ages, addresses, emails, purchases, transactions, browsing histories, and these customers are listed. If you were to rearrange the rows or rearrange the columns, the information itself wouldn't really be compromised. It would all still be there. It would all still be queryable, searchable, and interpretable. Convolutional neural networks don't help you here. They look for spatial patterns. So if the spatial organization of your data is not important, it will not be able to find what matters. So, rule of thumb, if your data is just as useful after swapping your columns with each other, then you can't use convolutional neural networks. You shouldn't use convolutional neural networks. That's a big takeaway from this. So they're really good at finding patterns and using them to classify images. That is what they are the best at. Now, the takeaway from this is not that you should go and code up your own convolutional neural networks from scratch. You can. It's a great exercise. It's a lot of fun. But when you go to actually use it, there are a lot of mature tools out there that are helpful and just waiting to be applied to this. The takeaway from this is that you will be asked to make a lot of subtle decisions about how to prepare your data and feed it in, how to interpret the results, and how to choose these hyperparameters for this. It helps to know what's going to be done with your data and what it all means so that you can get the most out of these tools. All right, good luck.